What is up, chemists? How is everyone doing today? My name is Wes Winter. I'm with Fiveable here to do your last CRAM before the AP test tomorrow. I hope you guys are so super excited. I know I am. I am so ready to get this going. So a couple of things I just wanted to prepare you and get you excited for today, but I think what would really make this session extremely useful for you is if you had a couple of things. So I'm going to list a couple of those things out, and then once I do that, Amanda's here to say some words for you. So while she's talking and saying some, great things about the company and all the stuff that's happening, I need you to have a notebook, paper, pencil, and pen, normal note-taking stuff. This is going to be a great way for you to kind of get some of your ideas out. I'm going to be going over some problems, so it'd be a great way for you to actually practice. Because if you're just sitting there and kind of absorbing, that's good. It's way better if you're actually writing things out and trying them out for yourself. Also, make sure you have a calculator today. We're going to be doing some FRQ type things, and you need a calculator for that. Don't forget to print out a periodic table and a reference sheet. It's just a quick Google search. Do AP Chem periodic table, AP Chem reference sheet. You don't want the first time you're seeing the periodic table and reference sheet to be on the test tomorrow. And that's pretty much it. Otherwise, the slides that we are going to be looking at are right below what you are on. I'm going to be doing some whiteboard work with you guys. And yeah, that's pretty much where we're at. So if you need to get a couple last minute things, the awesome founder of Fiveable, Amanda, is here to say a few words. It'd be rad if she walked in through here, but I think she's going to jump on through the stream right now. So Amanda.
What's up, AP Chem students? Amanda here from Fiveable. I'm the co-founder and CEO of Fiveable here in Milwaukee at the Fiveable house, not at Wes's house. But I wanted to pop in just to give you guys a couple of tips and a little tiny Amanda pep talk before we spend 5 hours reviewing every chem concept that you could possibly need. So 3 things really quick. One, if you have any concept or FRQ related questions, just pop them in the discussion thread below and TAs will be answering those questions as you go. If you have something that you want to ask based on what Wes is saying, just take a second and just wait until he finishes explaining it before you post. Because if we get bombarded in the discussion threads, we might have to change it up. So if something happens, you might get an email from me with an updated link, but hopefully we'll be all set. If you have any tech issues, though, just make sure to chat instead of asking on the discussion threads, because the student success team is ready to go to help you, but those are different than the TAs. Okay, and then the last update is that we're running a social media challenge like we did last year. So while you're here cramming in this night before your test, if you take a second, if you want to take a little break to post on social media, you could post on Instagram, Twitter, or TikTok about your CRAM experience. It could be something funny, something chem related, something calling out College Board's nonsense, anything like that. Just make sure to tag Yes We Cram, and we're going to be giving away $100 every single day to a winner. So you can play today. You can play if you're watching this as a watch party replay. You could play tomorrow after your exam. You can submit something anytime on any social media network. So I literally cannot wait to see those. Our social interns are going to be choosing the best of the best. And honestly, a lot of our social interns we hired because of this competition. So if you're really good at one of those social channels, now's your time to shine. All right. Lastly, I want to let you know that, first of all, I'm super proud of you. I know this has been a wild, insane year. There's a lot going on. No matter what happens on the test tomorrow, you make us so proud. You've been doing the work. You've been out here. You've been doing the thing. I know the stress levels are so high. So just take a minute, take a deep breath, and just say it out loud with me. I got this. I got this. You really do. You do got this. And no matter what happens tomorrow, we are so proud of you. You're part of the Fiveable family. Your score is not going to make or break you. What does is the fact that you are here. It's your resilience. And that ain't nobody can take away from you. Not College Board, no reader, no score, no wild, crazy question that shows up on the test. None of that can take away how hard you worked. So be proud of yourself for what you've done. We're proud of you, and have fun tonight. So Wes, I'll let you take it from here to kick it off with all 5 hours of chem review. See y'all later.
Awesome pep talk. I felt like half of it was for me. I'm like so happy and excited. I'm gonna do good. But with that being said, I think it's time to do some chemistry. I don't know about you all. I just wanted to first put this out there that I've been with Fiveable for 2 years, and I've really just loved every moment working with this crew. We've had also our ups and downs as well, and I just want to say thank you so much for letting me be a part of this. And yeah, like let's get into it. Let's do some chemistry. So the first thing that I really wanted to kind of just start us off with is boom boom boom. I'm just gonna share this. Of course, now I'm like stuttering. Cancel here. Boom, boom, and boom. So yeah, the first thing that I wanted to kind of go over is just who the heck am I? Well, my name is Wes Winter. I'm an AP Chemistry teacher. I've been teaching AP Chemistry for a long time. I've really enjoyed doing this. I got my degree in chemistry from UC Berkeley, go Bears. And I had just, a really fun time doing lab work, but I had way more fun teaching. I've always really enjoyed teaching. So I just want to say thank you so much for making this just such a cool job. I am also a drummer. I've drummed for a while. And I really love the outdoors. Funny thing is that I was in the marching band at UC Berkeley, where I met my fiance. We're getting married this summer. It's going to be super fun and really exciting. The pandemic definitely put a big scare on that, but we're still doing it. Woo! And so the last thing that I wanted to share with you, I know it's kind of a brief overview of who I am, but the last thing that I wanted to share with you is that I'm actually really excited to do this 5-hour CRAM today. I'm actually pretty excited about this. And the reason that I'm so stoked, so excited to do this is that I've actually had a lot of experience cramming for 5 hours, all the units of chemistry. One of my old jobs, I was an AP Chem tutor for the Bay Area tutoring centers over in the East Bay. Cool company if you're in Berkeley or San Ramon area. And we would do these crazy 5-hour reviews, 4-hour reviews, and we would shove everything we could in those sessions. So I have actually a pretty decent amount of experience doing this. And I just want you to know that I got you today. I'm like super stoked to cover as much of the material as I can. So our goal for today is the following. Basically, what I'm going to do first here is just make sure you understand what you're going to see on the test tomorrow. We are going to go over some tips and tricks for actually taking the test, what the test is going to look like, what you should expect, what you should be prepared for. And then we are going to do basically for the rest of the afternoon content review. Basically each hour I'm going to try to cover about 2 units. So in the first hour, I'm going to be looking at units 1 and 2. That's going to be looking at the atom and also chemical bonding. The next hour, we're going to be doing units 3 and 4, which is intermolecular forces, chemical reactions. After that, 5, 6, 7, 8, 9. No 10. There's no 10 units. Thank goodness. There's only 9. So with that being said, throughout our session today, I'm going to be throwing some stuff in. We're going to be playing a graph game somewhere in the middle here. I really enjoy this game. I think you guys will too. It's a way of kind of looking at graphs and trying to think about all the different graphs that we've seen this year and kind of how do we approach like a certain curve. Like when you see something on the paper, you're like, I know exactly what that looks like. So there's plenty of graphs in AP Chemistry that you should be comfortable with, and we'll talk about all of those as well. Last but not least, I will be peppering in many free response practice throughout our session today. Luckily, I will be able to kind of do a whole bunch of FRQs, just making sure that you are ready to do some AP chemistry. See those questions tomorrow. And yeah, that's pretty much where we are at. But you guys got a little bit about me. I kind of want to take a second and get to know you guys a little bit. And I kind of wanted to see how you're feeling. What's up with you guys? Where are you at? And so what I have here is a quick little form on mentimeter.com. So if you go to menti.com and use this key code here, you're going to see the first question, which says, where are you from? Now, if you're in the US, I want you to type in the state. If you're from out of the US, I would love for you to type your country that you're from. I just want to kind of get a smattering of where are you all at. I'm just so curious. I want to see kind of what places are we from. So go ahead and share when you have the opportunity to do that. And while we are waiting for responses, I know it's going to take a second or two to get here. Nice. Look at that. Here it comes. I want to kind of share with you guys a little bit about Unit 1. Unit 1 is going to be, right, the atom. We're going to be looking at what else? Electron configurations, and we're also going to be talking about Lewis structures in this first hour. We're going to be talking about oh goodness, what else? Ionic compounds and the like. So it looks like Florida and California are kind of tied. Look at that. Got some New York though. I want to see, is there any out of the country? Guadalajara, nice. Puerto Rico. Right on. I'm assuming the you-know-where is one of my students. All right, nice. We'll go ahead and let it go for 2-3 more seconds here. And great on Southern California. Love seeing all these responses. So I'll go ahead and share this again in a little bit. But yeah, it's so cool to kind of have this experience and see where all of you are from, So I think one of the things that we can go ahead and do is really just kind of jump into what the test is going to look like. If you didn't realize this, hopefully you do. The test is going to be tomorrow, May 7th, 2021. And there are other test administrations. And if you are here and you're taking the test on May 25th, or I believe it's June 10th, you're still going to get really great information. I do want to point out that the stuff you see over here on the right, will not hold up for the June test date. It will be good information for the May 25th test date, though. So just be aware that your test on tomorrow or at the end of May, this is what you're essentially going to be preparing for. So essentially, you're going to have 2 sections. You're going to have a multiple choice section, which will be an hour and a half long, worth 50% of your grade, and it's going to be 60 multiple choice questions. The big thing, and hopefully this is not news to anyone, but you are not allowed a calculator on the multiple choice section. So, and I do want you guys to be aware that even though there is not a calculator allowed, you still will be seeing a lot of quantitative type questions. Section 2 is the free response. You will see 7 questions. 3 are long answer, 4 are short answer. And what's kind of funny when they say long answer and short answer, it's not that your answers are longer, it's that there's more that you have to answer. Meaning that questions 1 through 3 usually have like anywhere from 5 to 8 parts. And then the questions, what would that be, 4 through 7 are the short questions. And you usually have like 2 parts or 3 parts, maybe sometimes 4 parts. The long questions are worth 10 points. The short answers are worth 4 points. One thing I do want to mention, I'm going to come back here, and I forgot to say this earlier. The multiple choice section, you are not penalized for answering questions incorrectly. So make sure you guess. I know, and don't guess. Hopefully you know the answer. But if you, for some reason, don't know the answer to a question, please make sure to go ahead and at least answer something. Put something down. Do not leave questions blank. All right, we'll come back down to the free response here. And I do want to remind everyone that you absolutely are allowed to use a calculator for the graphing part of the test, all right? So with that being said, the tips and tricks that I just kind of want to briefly go over here, make sure you have a calculator that you are comfortable using. please don't let tomorrow be the first time you're using a brand new shiny calculator. I know those are super exciting, but at the same time, you might not be prepared to use that. You don't necessarily need a graphing calculator, but if you're comfortable with using those, sometimes they can help you answer questions. Otherwise, just like the regular TI-20 calculators are perfectly fine. If your calculator requires batteries, bring some extra batteries. That would be the worst part of the AP test if you got there and you didn't have a working calculator. Make sure you have scratch paper, some sort of working writing device, periodic table and equation, and constant sheet. I do want to point out that the test provides the periodic table and equation and constant sheet, but make sure you know what those look like before tomorrow. Your test people may provide you scratch paper. They probably have to provide you scratch paper, but it's always maybe a good idea to have something nearby. Now, at the same time, don't put anything on that scratch paper ahead of the test date. Other than the writing utensil, the other stuff will be provided. Read the questions carefully. I hope that this doesn't come as a surprise, but if you don't actually answer the question, you might not get the points. They often will have some sort of direct point or thing that you have to answer. And sometimes they'll even say answer using this sort of calculation, answer using or describing this thing. For example, a lot of questions will say answer using Coulomb's law. If you don't say or reference Coulomb's law in your answer, you might not get full points. So make sure you answer the question, the direct question, and also read the questions carefully. I do want to point out that you should be cognizant of time. I know it's painful, but make sure you answer all questions. You are not penalized for incorrect answers, meaning like you won't be losing extra points for something incorrect. So make sure you don't leave anything blank. You should be cognizant of significant figures. Make sure to always answer at least with 2 or 3 sig figs if you're really struggling with the significant figures. But be very happy in the fact that really only one question on the AP test, specifically the FRQ, will assess significant figures, okay? So with that being said, make sure that you pay attention to sig figs to the best of your ability. If you're really struggling, then just answer with 3 significant figures, and that will get you kind of most of the way there. Once again, only one question actually assesses the sig figs anyway. I saw this last year, and the people that I've talked about with this have been really torn. So when we talked with some actual College Board readers, and one of the things they said was to not box your answer. I thought this was really interesting because whenever I'm working with my students, I always say, hey, make sure you box your answer. It makes my life a little bit easier. But the reason that the College Board reader said to not box the answer was that if the correct answer was somewhere else on the paper, but you boxed something else, they have to assume that that's your final answer. Once again, I think that this is an interesting tip and trick. I don't necessarily know which way is better, but if you make the decision to box your answers, that's fine. If you decide not to box your answers, that's also fine. Luckily, most of the College Board people are literate and they'll be able to read through your page. That also brings up, make sure you write clearly. Make sure they can understand what you're writing. Last but not least, or actually there's 2 little small tips here. If something is in parentheses, it's probably a hint. It's kind of weird, but they do like throwing these like parenthetical statements in and just saying like, hey, make sure you pay attention to this. The biggest hint that we'll talk about here in a few seconds is formal charge. They'll say, write the best Lewis structure, and they'll say in parentheses, consider formal charge. That hint's telling you to write the formal charge for each element in the structure that you're looking at. And last but not least, yes, and I've seen this question come up a few times, even though we've had a weird year where a lot of us have been learning at home, you still will be expected to answer experimental type questions. I know that sounds super frustrating and kind of confusing, but I am to this day believe that anybody who understands the experiments on a theoretical level can still do very well on the AP test. I do want to point out, though, that when they ask you to explain or kind of discuss what's happening regarding like error and stuff like that, human error is never an answer. And I can't even begin to tell you how many times my students will say, oh, or other students will say, oh, it's human error. Don't fall for that. It's never human error, all right? So that's where my test tips and tricks are at. And I really wanted to say, like, once again, make sure you also get some good sleep tonight. Make sure you're eating some good food tonight. Make sure you're getting ready to do this big thing tomorrow. It's kind of like a sports event. If any of you play sports, make sure that you eat some good food, stay hydrated, because tomorrow during the test, you don't want to be like, oh, atoms are cool. Oh, my tummy is hungry, right? Like, you don't want to do that. So make sure you do treat yourself well tonight. Make sure you do treat yourself well tonight. And now we're going to jump into the first unit. The first unit is atomic structure and properties. And what I'm going to do here in a second is kind of give you a brief list of what I plan on talking about. And then I'm going to jump over to my whiteboard. I'm going to jump over to my whiteboard. Now, as far as this goes, my whiteboard is has a downloadable. My whiteboard has a downloadable thing after the fact. So what's really cool is after today, I'm going to download all the stuff that we wrote and talked about, and I'm going to ship that image into Discord. So if you're following us on Discord, super awesome. Thank you so much. But that's a good place for us to be able to talk about what questions that you probably have. And I guarantee you, if you are a junior or younger, you're probably going to be taking some AP tests next year. So it's another place for you to start kind of collecting and gathering resources for your other AP tests, all right? So last thing, anything that I talk about in Unit 1 now is a good idea to maybe answer questions, or excuse me, ask your questions in the Fiveable Q&A area. Our awesome TA, Dahlia, along with I've seen a couple other TAs, are going to be helping gathering some of the information and then sharing those with me. Once again, I want to remind everyone that I've been doing these reviews for a very long time, and I'm really excited to do this. So I have the ability to kind of jump around a little bit and kind of discuss a few things. So here we go. Unit 1, Atomic Structure and Properties. So what's really cool about this is that we're going to be talking about moles and molar mass. We'll be talking briefly about mass spectroscopy, electron configuration, photoelectron spectroscopy, and the periodic trend. So these are going to be the big things that we go ahead and talk about. I don't know why that didn't open up here, but that's okay. Go ahead and open it up here. So this is what we're going to be talking about today. And once again, this would be a great idea for you to kind of think about, hey, I really didn't love that unit when we went over talked about it. Hey, I was really bad at mass spectroscopy, or hey, I don't even know what mass spectroscopy is. Don't worry, hopefully at the end of this half hour you will. So let's go ahead and jump into it here. And what we're going to do, what we're going to go ahead and talk about is an interesting element, an interesting atom. We're going to be talking first here about chlorine. So chlorine, if you look on your periodic table, so I'm going to be jumping through a couple things here, but here's my periodic table. And if you look, you'll see that chlorine is over here. And there's basically two pieces of information. You have the atomic number up top and the molar mass or average atomic mass down below. So chlorine's atomic number, we'll go ahead and start with that, is 17. So atomic number is 17. And the big takeaway for the atomic number is that it tells us the number of protons. So the number of protons that every single chlorine atom in the world is 17. Now, if chlorine was neutral, it would have 17 electrons. Now, as we know, chlorine is not always going to be a neutral atom. Sometimes it is charged, and we will get to that in a second. But at the end of the day, when you look at the periodic table and you see the atomic number, it tells you the number of protons. So quick concept check, which element has 23 protons? Which element has 23 protons? Give you a second to check your periodic table. And hopefully you're like, oh, cool, 23V for vanadium. I do want to point out that some of these elements don't have atomic or molar masses here. So technetium is one of them, polonium, radon here. These elements are not stable at on planet Earth, or really there's no stable nuclei, for these elements. So there's no average atomic mass. There's also, notice, no names for any of the elements on the periodic table. And you don't need to memorize these, but I would say make sure you're very comfortable with at least the first 36 elements. So chlorine has 17 protons, and a neutral atom of chlorine has 17 electrons. Now, the next subatomic particle, hopefully that you're comfortable with, is the neutron. And interestingly enough, this depends on which isotope of chlorine that we are looking at. So the next thing that we're going to quickly define here are isotopes. Isotopes are going to be atoms of the same element with different numbers of neutrons. So really, the neutron is just a subatomic particle that exists in the nucleus of the atom. It helps stabilize the atom. So for chlorine, there are two stable isotopes. For chlorine, there are two stable isotopes. We have chlorine 35, and we have chlorine 37, chlorine 35 and chlorine 37. These numbers off the end here are what are called the mass number, And the mass number is going to equal the number of protons plus the number of neutrons, the number of protons plus the number of neutrons. So as far as that goes, when we're checking out the number of protons and the number of neutrons, since we know that chlorine always has 17 protons, we can just subtract 17 from 35 and from 37 to find that chlorine 35 has 18 neutrons, while chlorine 37 has 20. And really what's fascinating about chlorine 35 and chlorine 37 is that they're roughly identical. These two elements are pretty much the same elements. They have the same maybe look, the same feel, the same reactivity. Since we're in chemistry, we love talking about reactivity. But at the end of the day, making sure that we're comfortable with the number of protons plus neutrons is how we get this number. The protons can always be found by looking at the periodic table. Now, the other really interesting thing about the mass number is that it's roughly equal to the mass of the isotope. So chlorine 35 has a mass of about 35 atomic mass units, or 35 AMU. Chlorine 37 has roughly a mass of 37 AMU. AMU is just a really small unit. AMU is just a really small unit that stands for atomic mass unit. And it's really only going to come up when we're measuring single atoms. Not the most important unit to have known or memorized, but it is kind of relevant when we're discussing isotopes, single isotopes, and especially in where we're going to go ahead and transition here. So if a single isotope of chlorine, so chlorine 35 weighs about 35, and a single isotope of chlorine 37 weighs about 37, I want you guys to consider these are the only two isotopes for chlorine that exist naturally. Let's go back over here to the periodic table. When we look at the periodic table, notice that chlorine has an average atomic mass of 35.45. 35.45 is neither 35 or 37, right? We said that chlorine has a mass of 35 or 37, but hey, what the heck? Well, where does this come from? Well, this kind of brings us up to our next concept here, our next big concept, which is the average atomic mass. Average atomic mass. The average atomic mass is the weighted average, boom, the weighted average of the naturally occurring isotopes. The naturally occurring isotopes. And what's cool about this is that we can clearly see that since chlorine's average atomic mass was 35.45, the more naturally abundant isotope would be chlorine 35 compared to 37, since, once again, the average atomic mass was much closer to chlorine 35. So once again, most of my chlorine is going to be 35 and not 37. So let's go ahead and quickly show you how to actually determine the average atomic mass given certain data for these elements. Well, when we look up chlorine's, there we go, chlorine's isotopic data, we find that chlorine 35 has a rough percentage of about 76%. So about 76% of chlorine is chlorine 35 in the wild, in nature. And chlorine 37 has roughly the rest of it. Now, if these are the only two isotopes, we know that percentages add up to 100. So quickly do that math in your head. What percentage of chlorine would be chlorine 37? Hopefully you got 24%. And basically with these two pieces of data here, we can quickly go ahead and determine how heavy, what the average atomic mass of a rough chlorine isotope is. Notice that not a single isotope of chlorine will weigh this, but on average they will. The average atomic mass will equal the mass of the first isotope times its abundance, which is 0.76, plus the mass of the second isotope times its abundance. And if you multiply these all out, you get roughly 36.4 AMU. Excuse me, 35. That was bad. 35.4 AMU. Beautiful. And that's our quick discussion on isotopes here. And once again, if you have any questions regarding isotopes, feel free to throw those into our discussion, and we can talk about isotopes in more detail. But I do want to kind of keep pushing our way through because we have so many units to cover today. So the next kind of cool thing that we can use with the 35.45 is the molar mass. So one of the coolest things, and I'm actually going to kind of stop sharing here for a second, just so I can have a cool, frank discussion with you guys. The mole is the coolest number ever. The mole, not the furry thing, by the way. And I'm sure every single one of your chemistry teachers made that joke. And if they did, you're welcome for making it again. The mole is defined as an Avogadro's number of particles. Avogadro's number is 6.02 times 10 to the 23rd. And hopefully you realize that this is massive. This is so big. This is probably one of the biggest numbers that you will ever come across. And there's a couple cool ways to think about this, but one of my favorite ways to look at this or consider this is that if you tried to count to this number, literally saying one number a second, so 1, 2, 3, 4, 5, I was even going fast there. How long do you think it would take to get to Avogadro's number? How long do you think it would get to 6.02 times 10 to the 23rd? And if you're saying 6.02 times 10 to the 23rd seconds, you're right, but that's not the point I'm trying to make. It would take longer to count to that number than the universe has currently existed. When we are talking about Avogadro's number, it is a massive number. And inside like a human, me, I'm made up of about 50 moles of atom. I'm made up of a just ginormous amount of atoms. So that's kind of one of the fun things that we discuss or think about here when we're talking about moles. Now, once again, one mole, sorry, it's still panning here. 1 mole is equal to 6.02 times 10 to the 23rd particles. And as far as this goes, this is its definition. For chlorine, we know that 1 mole of particles, which is 6.02 times 10 to the 23rd atoms of chlorine, it's going to have a mass of 35.45 grams. So something that's really cool that scientists did is they equated the number of the molar mass for chlorine to the average atomic mass for chlorine. So essentially, the molar mass means something else than the average atomic mass, but they are the same number. And this is a very valuable, kind of cool thing for us to take away from this. So a quick little practice here with moles, one thing we can go ahead and look at is a question like this. What is the mass of, let's say, like 1.25 times 10 to the 24th molecules? So a molecule, right, is a type of particle of carbon dioxide, CO2. Now, luckily, on the AP test, they will often provide you with the molar mass, but technically not always. They won't always provide you with the molar mass. So what you need to do is first, in a question like this, look up the molar mass of carbon dioxide, or identify the molar mass of carbon dioxide. So the way you would go ahead and do that is by molar mass would equal the molar mass of one carbon. So we have 1 times 12.01, plus we have 2 oxygen, so 2 times 16. Now, if you're wondering where I got the 12 or the 16 from, well, if we go back to our periodic table, we can see that carbon here has a molar mass of 12.01 grams per mole, and oxygen has a molar mass of 16 grams per mole. So essentially, essentially 12.01 for carbon, 16 for oxygen. We can go ahead and quickly calculate this and find that the molar mass for carbon dioxide is 44.01 grams per mole. And this becomes a conversion factor. What it is a conversion factor between moles and mass. So the first thing we're going to go ahead and do here is take my 1.25 times 10 to the 24th molecules of carbon dioxide and convert this to moles. Now, I know that for every 1 mole of carbon dioxide, CO2, there are 6.02 times 10 to the 23rd molecules. This brings me to my first kind of important point, and hopefully, once again, this is one of those things that you already know, but in case you didn't, the molecule is not the same as the mole. The mole is kind of like the dozen, where it's basically a number that represents another number. Whereas the dozen, right, equals 12 things. 1 mole is equal to 6.02 times 10 to the 23rd. Now that I have moles here, I can use the molar mass, which I calculated before, which is 44.01 grams per mole. And if I do this quick little calculation here, I can go ahead and find that the mass of 1.25 times 10 to the 24th molecules of carbon dioxide is going to be 91.4 grams. Moles and moles cancel out here. And one of the cool tricks for significant figures that I like to use and make sure I tell my students is that the number up front, so there are 3 significant figures here, is the number of significant figures that I have in my final answer. Once again, don't lose sleep over sig figs tomorrow. You should try your best to answer with sig figs, and definitely don't write the entire number that you have in your calculator out. But yeah, significant figures is not going to be a huge part of the test. Just make sure it's close. Make sure it's close. All right, cool. And the last little thing that I want to do regarding moles, let's go down this way here. The last little thing I wanted to do regarding moles was to talk about the percent composition and empirical and molecular formula stuff. So, and a question, there's a couple ways that we can kind of show you how to do this. So let's say we're looking at a compound with chlorine and fluorine, and they tell you that this compound is 38.3% chlorine, and this compound is 61.7% fluorine. Well, in a situation like this, you guys should get pretty excited, because the first thing you do when we're trying to determine the empirical formula is you just change this to grams, you assume that it is a 100-gram sample. So if we have 100 grams, what is 38.3% of that? 38.3 grams of Cl. If your substance is 61.7% fluorine, then you know it's 61.7 grams of fluorine. Now, this question is going to ask you something along the lines of this. What is the empirical formula? Now, remember, the empirical formula is representing the molecule in the lowest whole number ratio, So if we're looking at chlorine and fluorine here, we basically want to find out how many chlorines and how many fluorines are in the molecule in the lowest ratio. The way you do this is the same every single time. You are first going to convert this to moles. So for chlorine, we know it has a molar mass of 35.45 grams per mole. And for fluorine, if you look on the periodic table, it has a molar mass of 19.0 grams per mole. When you do this division here, we find the number of moles of chlorine in the sample, which is going to be 38.3 divided by 35.45 to get us 1.08 mole of chlorine. And this one down here, 61.7 divided by 19, gets us 3.24 moles of fluorine. The last thing you need to do for determining the empirical formula is essentially create the ratio. Right now, we know that our compound is 1.08 moles of chlorine for every 3.24 mole of fluorine. The way I figure out the whole ratio, the whole number ratio, excuse me, is by dividing each of these by the smallest number, which in this case was 1.08. When we do this, we find that this number is 1 and this number is 3. The ratio of chlorine to fluorine is going to be 1 to 3. And our ratio, boom, here we go, is this. Now, the last thing that I want to go ahead and cover about Unit 1, I know we are like already there. We are screaming through the units, but that's because we have, eight more units to go today. Yay. Is electron configurations. So with the electron configurations, you just need to be comfortable doing the electron configurations and relating them to the periodic trends. So let's go ahead and jump into that. Let's talk about electron configurations here. Ooh, this document is going to be kind of fun. Let's just go straight down. We'll have a really long document. So electron configurations, first off, I just want to make sure you guys are aware. So I do that every time. No, I hit the draw thing, the pen. There we go. Electron configurations are just a way to describe how do I want to say this? It's basically listing where the atom's electrons are located. So for example, chlorine's electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6. And as far as this goes, you can quickly identify where the elements are on the periodic table, into their respective blocks. So we have over here, this is my S block. In the middle, this is my D block. Over here, and notice I didn't include helium in that. This is my P block, and then down below, it's the F block. And what we're going to do is read top to bottom, left to right, filling each respective energy level and sublevel with electrons. What are energy levels and sublevels? Well, let's go ahead and talk about that. So an energy level, and I literally want you guys at home to repeat after me, okay? An energy level describes the distance of the orbital from the nucleus. Go ahead. Energy level is the distance of the orbital from the nucleus. Yeah, see, I know you all said that with like kind of like a Oh my God, I can't believe this guy is making me say it. But it's helpful because if you know that the energy level is relating the distance of the orbital from the nucleus, you are like halfway there with most of the explanation type questions. Once again, distance of the orbital from the nucleus. Now, as far as the orbital goes, the orbital is going to be a region in space where the electron spends 90% of the time. Sorry about that. Orbital here is a region in space where the electron spends 90% of its time. And there are a couple different orbitals. There are a couple different orbitals here. But the orbitals are mostly the s, p, d, and f orbitals. The s, p, d, and f orbitals. The s, p, d, and f orbitals are just different shaped orbitals. And there's a couple things that I want you to know about them. There's a couple things that I want you to know about them. What I want you to know is the following. First off, what the orbital is. So S, P, D, or F. The shape of it, which is spherical, dumbbell-shaped, four-leaf clover, or just, complicated, don't worry about it. It's a big kind of crazy orbital. The number per energy level, NRG level. So there's one s orbital per energy level. There's 3 p orbitals per energy level. There's 5 d orbitals per energy level. And there's 7 f orbitals per energy level. And last but not least, you need to know that all orbitals can hold up to 2 electrons. All orbitals hold up to 2 electrons with opposite spin. So as far as this goes, the s orbitals can hold up to 2 electrons. The 3 p orbitals can hold up to 6 because 3 times 2 is 6. The d can hold up to 5, and f can hold up to 7. So if I quickly pan back over here to my chlorine, I see that chlorine has 2 plus 2, 4, plus 6, 10, plus 2, 12. The electron configuration is incorrect, which I think is the Discord message I probably got. Yeah, I just noticed that. Thanks, Dahlia. So really quickly, sorry, as I quickly went through this, this here is not 6. It is actually 5. And what a crack up. That's my first one of the night, but that's okay. Hopefully it'll be my only one for tonight. The chlorine here, once again, is 1s2, 2s2, 2p6, 3s2, 3p5. And what we did is we indicated the location of 17 electrons. There are 2 electrons in the 1s orbital, 2 electrons in the 2s orbital, 6 in the 2p, 2 in the 3s, and 5 in the 3p. Once again, what does the energy level tell us? The energy level describes the distance of the orbital from the nucleus. So this number up front here is really close to the nucleus. 2 is a little bit further away. 3 is even further away. These 2 electrons are in a spherically shaped orbital, these ones as well as these ones. And then the p orbitals, the p electrons are in dumbbell-shaped orbitals. They are in dumbbell-shaped orbitals. So as far as this goes, we can relate the energy level to the periodic trends. Now, there are a whole bunch of periodic trends that you've probably gone through and talked about. I'm just going to talk about the big 2, which is atomic radius and ionization energy. Atomic radius is essentially the size of the atom. There is a funky definition in your textbook, but at the end of the day, just knowing how large or small the atom is pretty much good to go. It is from the center, from the nucleus, to roughly the outer-ish edge of the orbitals. That's hard to define in that way, though, because there isn't really an edge to the atom, right? It's just where the electrons electrons are kind of zooming around. And that's why your textbook has the rough definition. So I'm going to put this in quotes here, but it's roughly the size of the atom. And our other definition is ionization energy. Ionization energy is referring to the amount of energy required to remove an electron. The amount of energy required to remove an electron. This one I won't put in quotes here. Sorry, I keep panning it a lot. I'm still apparently not comfortable switching between the pen and the pan. Pen and the pan, well, that's hard. There you go, pen and pan. Those are hard words to say together. Ionization energy, amount of energy required to remove an electron. Amount of energy required to remove an electron. So as far as this goes, elements that are elements that have electrons further away from the nucleus are going to be larger, so the atomic radius is going to be bigger, and those electrons are more easily able to be removed, right? The idea is that the further the electron is from the nucleus, then the easier it is to be removed. So when we compare two elements that are in different columns, for example, something like lithium versus sodium, we can see that lithium has an electron configuration of 1s2, 2s2, 2s1, while sodium has an electron configuration of 1s2, 2s2, 2p6, 3s1. The valence electrons for sodium versus lithium are in different energy levels. And once again, say it with me, the definition of energy level is the distance of the electron from the nucleus. If sodium's electrons are further away from the nucleus, then they are going to be significantly easier to be removed from the atom. Also, sodium, having electrons that are further away from the nucleus, are just going to be larger. They're going to have a greater atomic radius. And this is where I'm going to go ahead and pause here and kind of see how you guys are feeling. Dahlia, once again, thanks so much for sharing with me in Discord. And I'm looking over here on the Q&A, just kind of seeing where we're at, what we're feeling, how you guys are doing with these types of questions. And by the way, if you know an answer to some of the Q&As, feel free to throw in your questions in there too. You can also, don't forget, you can also upvote questions so I can make sure to see them as well. Cool. All right, we are crushing it. We are doing so well. There is one last thing I wanted to show you from Unit 1, and that's the Photoelectron Spectroscopy. And for every year, we usually will go ahead and see some sort of FRQ. You'll definitely see a multiple choice question relating to this. So what I've done is I pulled one of the free use questions off of the College Board site for us to go ahead and check out. And that's right here. So from the 2019 test, we can see this question. The complete photoelectron spectrum of an element in its ground state is represented below. What I love about these, what makes me so super pumped when I look at a question like this, is that this will automatically tell me the electron configuration. The leftmost peak will always be referring to the 1s peak, and any peak that in general shares the height with it will also be an s peak. Now, I do want to point out that other peaks can have the same height because the height refers to the number of electrons. So if you just go in the relative order that you fill electrons in, we know it's 1s first, and there are 2 electrons there because you have to fill all those electrons in the lower energy level first. Then it's 2s2, 2p6, 2p6. Let's go ahead and erase that there. Oh, what did I do? That was funny. That's funky that it does that. 2p6, 3s2, 3p6, 4s2. See, now I'm just going to erase this here so I don't have to. 4s2. And you can write right on the graph as it shows it to you. It's a great little trick for you to kind of work your way through these here. And then when it says identify the element, there's a couple ways to do this. You can look at the relative block on the periodic table. We know that this block here, right, is 1, 2, 3, 4. So 4, we know it's in the S block here, the S block. S and 2, so it's going to be calcium. This element here is going to be calcium. And based off of this, we're able to answer question A part I and question A part II from the FRQ question in 2019. Now, there are a couple other questions that could come from this as we're looking at the numbers down below. I can tell you that this question then goes on to ask about light, which I will cover in Unit 3. So I'm going to go ahead and close this out here and just say, awesome job with Unit 1. We did it. Woohoo! And I want to show you how they like questions being answered. So for question part A, part I, we can see that all you need to do is write out the electron configuration. It says 1 point is earned for the correct answer. And the next part says identify the element, and it's calcium. You can write literally just Ca, and you get 1 point for the correct answer. Unless it says like justify the answer or like do math or, you know, et cetera, et cetera, et cetera. Just write calcium and the electron configuration. Don't spend time like saying the electron configuration is 1s. Don't write full sentences when it's not necessary. And bam, that's Unit 1. I want you guys literally like to kind of stop for a second and go, whew, take a deep breath. All right, that's all the time I can give you because we have to do Unit 2. Luckily, Unit 2, really the only thing we need to cover for this is Lewis structures, and we also need to go over just the different types of properties that you should expect to see for the AP test. And really it's, yeah, how do you draw Lewis structures, and can you recognize different types of properties or substances here? So voila, Unit 2 is the molecular and ionic compound unit. We're going to be talking about ionic compounds. We're going to be talking about metals and alloys. We'll be talking about molecular compounds, and we'll be talking about Lewis structures. I'm going to quickly cover a couple of examples here, but what I have down below is absolutely what you need to know regarding charge on the periodic table. Everything in the first column here has a 1+ charge. Everything in the second column has a +2 charge. Over here, +3, -3, -2, -1. And these 4 positions you just need to know. So zinc is right here, always has a 2+ charge. Silver, which is right here, always has a 1+ charge. We have tin and lead, which can either have +2 or +4, depending on what they are bonded to. And you can usually determine what their charge is based off of the ratio or the charge of the other thing that they are bonded to. So what I'm going to go ahead and do here is actually give us a couple of examples. So we are once again are moving on to Unit 2. I will click on the pen one of these days. Unit 2. And what I'm going to go ahead and do is go through 3 different substances here. So what we're going to do is we're going to look at sodium chloride, NaCl. We're going to look at carbon tetrachloride, so CCl4. And then we're going to go ahead and look at our friend gold, AU. Fun story. My high school chemistry teacher had a goldfish named AU. Ha 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 ha, knee slapper. This is the kind of chemistry teacher I want to be, guys. I'm one day going to have a goldfish, and he's going to be named AU, and I will think of my chemistry teacher forever and always. All right. So being able to recognize the type of bond that exists within these substances here is probably one of the more important things when recognizing substances. If you have just like we'll go ahead and draw up here like kind of short little periodic table. So boom, boom, boom. So here's my periodic table. Voila, very well done, right? It's cut in half by this staircase. The staircase are the metalloids, Anything to the left of the staircase are going to be metals. Anything to the right are going to be non-metals. Non-metals. You're not going to let me write the L. Scooch over here. The non-metals are the lesser of the periodic table. You'll notice that most of the periodic table are metals. And each one of these, depending on if they are by themselves, combined, or once again by themselves, they have different properties. And what they are looking at is the different types of chemical bonds that exist within them. So for example, sodium chloride is a combination of a metal and a non-metal. These are going to contain ionic bonds, contains ionic bonds. And as far as ionic bonds go, these are going to be the attractive force between oppositely charged ions. And so what essentially happens here is chlorine is more electronegative than sodium is. So it will be able to attract the electrons from sodium, essentially taking the electrons away from it. This means that sodium is positively charged and chlorine is negatively charged. The relative charge particles allow for a couple of interesting properties to arise. Ionic compounds are fairly hard but brittle, meaning that they are easily broken, but they are pretty rigid. They have very high melting and boiling points, and they conduct electricity when dissolved into water. Conduct electricity when dissolved in water or in the liquid state. In water, H2O, or molten. So we say molten because they have really high melting and boiling points. So as far as NaCl goes, relative to CCl4 and possibly Au, it's going to have a pretty high melting point. It's very hard but brittle. And once again, they can only conduct electricity when they're dissolved into water or when they're in the molten state. CCl4, notice, is composed of two nonmetals. So this contains covalent bonds, And we'll talk about the different types of bonds as well, covalent bonds. But when we are going, that's a gross B. Let's redo that. Yeah, a little bit better. So as far as containing covalent bonds goes, we know they are covalent bonds because the nonmetals are bonded to each other. Nonmetals have really high or large electronegativities, and because of this, they can go ahead and essentially share their electrons. So what they're doing is sharing electrons. And because of this, there's not really any charged particles holding them in. So relative to ionic or metallic substances, covalent compounds have really low low melting and boiling points. Carbon tetrachloride is a liquid at room temperature, but it's pretty easy to raise the temperature and allow for this substance to evaporate. Last but not least, it does not conduct electricity pretty much ever. There's one small subclass of covalent compounds, that can conduct electricity. Those are the acids, and we'll talk about those before the end of tonight. Okay, so it does not conduct electricity. And the really quick little subsection of bonding that I want to discuss in a little bit of detail here is Au, or just gold in general. Now, when we're talking about gold, or really anything that is from the metal side, these are going to contain what are called metallic bonds. Let's go ahead and use purple here. Contains metallic bonds. And really what's going on with the metals is that they have such a low electronegativity that the metals are pretty like free-flowing and willy-nilly with their electrons. They don't care who has their electrons. So because of this, the bonding model is called the sea of electrons model. And what this is saying is that quite literally, like the sea, electrons are free to flow around. So if I have my Au atom, Any electrons that these have are able to flow freely between one metal atom and the other. And this allows for a couple really cool properties to arise. Metals are malleable and ductile. So if you ever see these words, by the way, it's referring to the metallic substance. They have high luster, they're shiny, and they also are very good at conducting electricity and heat. Electricity, and we'll go ahead and pan here, and heat. And so that's just a quick little overview of anything that contains ionic bonds will generally be hard but brittle. Anything that contains covalent bonds will generally have a low melting and boiling point. Anything that contains covalent bonds will also never really conduct electricity. Ionic compounds cannot conduct electricity in the solid state, but they can do so in the liquid or molten state / when they're dissolved into water. Metals, or things that contain metallic bonds, are described using the sea of electrons model. And essentially, when we're going over this, the key words you want to look out for when we're talking about metals are malleable, ductile, and luster. Metals can pretty much always conduct electricity and heat. And these are the best ways to define the types of bonds that exist within them. Now, I do have a quick FRQ that we can discuss / go over when we get to ionic compounds. So what I wanted to go ahead and do, what I wanted to go ahead and end with here in terms of Unit 2 was how to draw Lewis structures and some of the interesting things that arise from this. So let's go ahead and jump into it here. Steps for drawing Lewis structures. Steps for drawing Lewis structures. Boom, boom, boom. Lewis structures. Fun fact, I got to learn how to draw Lewis structures in the Lewis building at UC Berkeley. My students are totally going to be making fun of me for this, but I don't really care. I always love to talk about UC Berkeley. It was such a fun school. It was such a fun experience. And seriously, wherever you guys end up going to college, you're going to have so many really fun, interesting facts. So my fun, interesting fact is that G.N. Lewis, Gilbert Lewis, was a professor at Berkeley, and yeah, he has a building there named after him. All right, step number 1. You want to count the total number of electrons. Total number of valence electrons. So when we are looking at the periodic table, so I'm going to step away from this really quickly here. But the valence electrons are actually quite easy to count on the periodic table. All you have to go ahead and do is write across the top 1, 2, 3, 4, 5, 6, 7, and 8. This doesn't include helium. Helium has 2 valence electrons, but everything else in this column has 8 valence electrons. So when we're counting the number of valence electrons for drawing Lewis structures, that's all you got to do is you got to count from the left to the right. Hydrogen always has 1. Nitrogen has 5. Oxygen has 6. Bromine has 7. Germanium has 4. And you're probably now asking, well, what about these guys down below here? You don't have to worry about counting number of valence electrons for these for a couple of reasons. One, the way the electron configuration works out is that you don't necessarily need to go over this. And 2, you're never going to draw Lewis structures using metals. So we really only do Lewis structures for the things over here, the nonmetals and hydrogen, because Lewis structures are representing how covalent molecules are forming bonds. So as far as that goes, we want to count the total number of electrons. So let's go ahead and try this out. I'm going to do one off to the side here. We're going to do SF2, sulfur difluoride here. And, actually, you know what? I'm going to take that back. We're going to do SF4. We're going to do a funkier one here. And so count the total number of electrons. So sulfur, right, has 6 valence electrons. Fluorine has 7. So sulfur has 6, fluorine has 7. And there are 4 fluorine atoms. So 7 times 4 is 28. Plus 6 is 34. So our drawing must have 34 valence electrons. Where did I get 38 from? Who knows? All right, so after you count the number of valence electrons, you then want to determine the central atom. As far as this goes, it's usually pretty straightforward. Determine a central atom. So in this case, it is sulfur. But basically, the central atom is the atom that every other element will bond to. So sulfur is going to bond to 4 fluorine atoms. Otherwise, it's always going to be carbon. It's never hydrogen. Hydrogen only wants single bonds. And yeah, you're pretty much good to go with that. Draw all atoms single bonding to it. All atoms single bonding to it. So as far as this goes, that's step 4. We're going to have 1, 2, 3, and 4. What I just drew here are actually some valence electrons. I drew some electrons here. So the whole point of this over to the side is I am paying attention to the total number of electrons that I can have in my drawing. The easiest thing that you can do is count the total number of valence electrons. And if your drawing at the end doesn't have the right number of valence electrons, then your Lewis structure is incorrect. It has to have 34 valence electrons. So I just drew 8. That means there are 26 more available. I then want to go ahead and add valence electrons to the exterior atom. Add valence electrons to the exterior atoms, satisfying the octet. Atoms. Satisfying. I can spell satisfying, I promise. Satisfying the octet. So as far as this goes, fluorine needs 1, 2, 3, 4, 5, 6. And then I'm going to do that 3 more times. So 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So my drawing now has a total of 32 electrons. I need to put 2 extra in there. And that helps me with my second to last step here, which is all remaining valence electrons go on the central. All remaining, that's not how you spell remaining. Remaining valence electrons go on the central atom. So in this case, we have 2 extra electrons, and you can just put them as a pair on the central atom. And this is the final Lewis structure. Now, there is one last thing that I want to go ahead and add here. I'm going to go ahead and slide this down here. Any remaining if your central atom has less than 8, if central atom has less than 8, then 8 valence electrons, then what you need to do is make double or triple bonds. Make double or triple bonds. And I'll show you what that looks like here in just a second. But notice here, my sulfur has 2, 4, 6, 8, 10. It has more than 8 valence electrons. So we are good to go in that regard. We're good to go in that regard. All right, let's go ahead and check out another one. So that's my final Lewis structure for SF4. Let's go ahead and do one more here just to make sure we're comfortable with this. We're going to go ahead and look at hydrogen cyanide, which is HCN. HCN. And once again, as far as this goes, we first want to count the number of valence electrons. So hydrogen has 1, carbon has 4, nitrogen has 5. And if you need a reminder, 1 for hydrogen, 2, 3, 4, 5 for nitrogen, and 4 for carbon. As far as this goes, let's go ahead and change my color up here. I need to then determine what my central atom is. It will pretty much always be carbon, so carbon's my central atom. Nitrogen is one of the exterior atoms. Hydrogen is the other. So I forgot to add these up. Sorry about that. 1 plus 4 plus 5 is equal to 10. and I just drew 4, so I have 6 valence electrons left. Now, this is super important. I want to make sure everyone hears this. Hydrogen will never have lone pairs around it. The Lewis structure for hydrogen will always just be a single bond to something. So hydrogen is notice single bonding to hydrogen. There's never a situation where it will have a double bond or 2 atoms bonded to it. Hydrogen will never have that. It will never have lone pairs around it either because it doesn't follow the octet rule. In order for it to have a full energy level or shell of electrons, it only needs 2 electrons. So what I'm going to go ahead and do is add these 6 electrons over here. So 2, 4, 6. And I'm out. I'm out of valence electrons. So rule number 6 here is kind of applying to something like hydrogen cyanide, where my central atom has less than 8 valence electrons, and therefore I need to make double or triple bonds. The way I do this is actually super fun. I'm going to change my color here so you can see it. I'm going to take 2 electrons here and form and move them on the inside. So I remove them from nitrogen and move them from the inside. Notice that carbon now has 2, 4, 6 valence electrons. So it doesn't have 8 yet, but what I can do is remove the exterior atoms again inward. Now I have 2, 4, 6, 8 for carbon. I have 2, 4, 6, 8 for nitrogen, and my Lewis structure is complete. Essentially, when I'm doing these, I want to make sure that my final drawing, once again, has the total number of valence electrons it's supposed to have. So in this case, it's 10. So 2, 4, 6, 8, 10. And the octet is satisfied for as many exterior atoms as possible. So for nitrogen, it's satisfied. For hydrogen, it doesn't follow the octet rule. And the central atom may have, so I'm going to go back to the periodic table here. The central atom may have more than 8 valence electrons as long as it's in the 3rd period or below. So nitrogen, carbon, oxygen, and fluorine cannot have more than 8 valence electrons. They can't have a hyperoctet like sulfur did in the last example. Notice that sulfur up here did have more than 8, but that's because sulfur is in the 3rd period. Alrighty-o. So now that we're feeling like we are pros at drawing electron configurations, I want everyone to like do a little arm dance. Like, oh, I know that's super gross because you see all my arm flab, but whatever, because you need to do it, right? You need to kind of like get loose, kind of relax. We've done about 2 units here. We are going to jump into a couple of FRQs for unit 2, but yeah. Hopefully you guys are feeling a little good. We'll do something else here in a little bit to kind of get our jitters out, but hopefully you are all crushing it. Hopefully you're all feeling really, really fantastic. So on to the FRQs, here. So if we jump over here, we'll actually see our first one. And what I'm going to do with this FRQ is kind of show you how to answer this question in the middle, and then I'm going to give you a couple of important details in a chart in a second here, like a VSEPR chart. And I hate to break it to y'all, but you really just need to memorize it. I'm sure there's a lot of mnemonics and kind of cool things out there, but you just need to memorize it. It's one of those things that comes up, and it's a free question if you have the VSEPR chart memorized. So here we go, boom, boom. So hydrogen, oxygen, nitrogen, and oxygen, HNO2, I want to draw the Lewis structure for this. I know that hydrogen has HNO2, 1 valence electron. I know that nitrogen has 5, and I know that oxygen has 6. So, but there are 2 of them. So that's going to be 18. I want my final Lewis structure to have 18. So what I'm going to do to make my life a little bit easier here is I'm just going to draw single bonds between everything. What did that do? Well, that basically accounted for 6 of the electrons. I now need to add 12 more electrons. Well, oxygen and nitrogen here are kind of like central atoms, so I'm going to go ahead and not add electrons to those, but I'm going to add 2, 4, 6 electrons to oxygen here, and that's going to go ahead and leave me with 6 more. And then I'm just going to put 1, 2, 3, 4 on oxygen, and then 1, 2 on nitrogen. Now, as far as this goes, that's all the electrons that I have. And there's kind of an issue here. Nitrogen, right, has no more electrons to share. It doesn't have any, it doesn't have an octet, is what I meant to say. So as far as this goes, I need to move electrons from an exterior atom. So remember, this oxygen on the left is not an exterior atom. It's actually a central atom. So I'm going to take 2 of these electrons here and scooch them in, and I'll keep my color back to red here. Or what we can do is kind of make the eraser. Sorry, I don't know why it does that. And I can go ahead and erase that. And my final Lewis structure will look like this. Now, one thing that I want to make you guys feel very comfortable with is, like, let's just say I screwed up and I accidentally drew the wrong Lewis structure. Hey, sometimes mistakes happen. Hopefully not tomorrow, but once again, it could. This next question here relies on you drawing that Lewis structure correctly. If you don't answer this part I correctly and then answer part 2 or part II based on the Lewis structure you drew, that is totally okay. They will accept it as long as it's correct based on your Lewis structure that you drew. We'll come back to this because what I want to quickly do is talk about shape, bond angle, and hybridization. So every Lewis structure that you will look at has the following things coming off of an atom. It either has a group of bonds, and I'll go ahead and pluralize this, but it could be a single, double, or triple bond, and a number of lone pairs. And both of these are on the central atom. And you can get a couple of things off of this. First off, we can get the shape. And we can also get the hybridization. Switch this over a little bit more. And the hardest question I've ever seen on the AP test was relating to hybridization, was written once again right here, right there. Identify the hybridization. And so when you get that, you go, yay, that's the hardest hybridization question that can come up. So I'm just going to quickly fill out a couple things here, describing them as I go. So as far as this goes, if I have 2 things bonded to the central atom with no lone pairs, this molecule is going to be linear, not lineal, linear, and have a hybridization that is sp. Notice that if I scroll back over here to my HCN, the central atom had 1 set of bonds and 2 set of bonds. Notice that it's not 1, 2, 3, 4, it's a set of bonds. Let's go ahead and actually write that so we don't confuse anyone. Set of bonds, I like that. So there are 2 sets of bonds. So that tells us that the shape around carbon here is linear, and the hybridization around carbon is sp. And that's the hardest question that you will have. Now, as far as hybridization go, in case any of you are curious, it is the mixing of atomic orbitals in order to make new molecular orbitals. Up next is going to be the 3-0 situation. This is going to be trigonal planar. And as far as this goes, this will always be sp2 hybridized. Next is 2-1, and this is going to be bent with a 120-degree angle. This is also sp2 hybridized. And what I want to point out is that if you sum up the set of bonds and the lone pairs, you will get the total number of orbitals that are hybridizing. Notice it's 1s and 2p orbitals, and the sum is 3. So we should have 3 orbitals hybridizing. And as long as you know that the only possibilities are sp, sp2, or sp3, you're pretty much good to go. So the last couple things for this chart are going to be as follows. We're going to have 4 and 0 for tetrahedral. This is going to be sp3, right? Because 4 plus 0 is 4, so we have 4 orbitals. 3, 1, which is going to be trigonal pyramidal. sp3. This is going to be a big chart here, so I'm just going to forewarn you. 2 and 2. This is bent with a 109-degree angle, sp3 as well. And then the last couple ones are based off of the 5-0. Now, what I want to say is that back in the day, the hybridization for this existed / we thought it existed, but there's been further studies showing that the d-orbital hybridization does not exist. So 5-0 combination, making a trigonal bipyramidal. For 1 is literally called seesaw. Yay. 2 is going to go ahead and be T-shaped. And the last big one is going to be 6-0, which is octahedral. So just making sure that you realize that they will only ask you about hybridization for one of these combinations here. The other ones listed down below do not have hybridizations associated with them, and they will not ask you that. So yay, they will not ask you that. So what I want you to do is look at, there we go. I want you to look at our Lewis structure here. I'm gonna give you about 10 seconds, and I want you to see if you can identify, what is the hybridization based on the Lewis structure that I drew here? What is the hybridization? All right, hopefully you see there is 2 sets of bonds with 1 lone pair. And so what that will tell us is that the shape around this is bent with a 109-degree angle. I don't know why it does that. Sorry about that, y'all. Bent with a 109-degree angle. And the hybridization associated, nope, sorry. With a 120-degree angle. That will never stop. I don't know why. 120-degree angle. And the hybridization associated with that is sp2. Up next, we could ask you questions along the lines of what is the shape, which we kind of had here, and a formal charge, which I want to go ahead and actually talk about with this structure here, okay? So hopefully you guys are still doing good. We're going to answer one more FRQ here in just a second as well. But I wanted to go ahead and dive just a little bit into more detail regarding formal charge and kind of look at this structure here in a little bit more detail. So when we look at these Lewis structures, once again, you need to remember that these Lewis structures are our best guess, our best combination for how these molecules and atoms bond in space, So as far as these Lewis structures go, they could have a different way in which the electrons are arranged, and we call these resonance structures. A resonance structure is just going to be when there is more than one acceptable Lewis structure. And as far as this goes, not all Lewis structures have more than one acceptable Lewis structure. Sometimes the Lewis structure that you draw is the only acceptable one. A good example that I can show you, though, would be sulfur dioxide, SO2. So this Lewis structure ends up looking like this, where we have sulfur with oxygens having lone pairs on either side, and then a single lone pair in the middle. Now, what is the issue here? Well, the issue is that my central atom has less than 8 valence electrons, and my central atom always needs at least 8. And what was the trick? Well, I can go ahead and remove 2 electrons from the outside forming a bond on the inside, a double or triple bond on the inside. But which side do I choose from? Well, in this situation, I could choose from either the left or from the right. And these two Lewis structures here are going to be equivalent. Whenever you have an equivalent Lewis structure, that's going to be when you have resonance. So as far as this goes here, these two are what are called resonance structures for each other. Now, resonance structures can have better or worse forms, if you will. And the resonance structure quality can be determined based off of the formal charge. Now, the formal charge is just a number identifying which element or which Lewis structure is the best. And your goal is to get all the formal charges to be 0. We want a formal charge of 0. Formal charge of 0. Now, a quick little cheat sheet for how to find formal charge. Formal charge will always equal to the number of valence electrons the neutral element has minus the number of dots minus the number of lines surrounding it. So for example, for sulfur here, sulfur on our periodic table normally has 6 valence electrons. So it's going to be 6. Let's go ahead and write this down here. So formal charge for sulfur is going to be 6 because it has 6 valence electrons, minus 2 dots, right? Because that's how many dots there are, minus 3 lines. So the formal charge for this is going to be positive 1, 6 minus 2 minus 3. The formal charge on the left for oxygen A versus oxygen B, so formal charge for oxygen A is going to be 6 because oxygen has 6 valence electrons, minus 4 dots minus 2 lines is 0. And the formal charge for oxygen B is going to be 6 minus 6 minus 1. And this is going to go ahead and be a formal charge of -1. So did we get our goal of having a formal charge of 0 on all of the elements? Unfortunately not. And as you can see, you can also kind of flip it around here. The formal charge for oxygen would be -1, sulfur +1. I'll put these in like parentheses here. And for oxygen, it's 0. So these Lewis structures that I've drawn here are not the best resonance structure. And remember, sulfur can have more than 8 valence electrons because it's in the 3rd period or below. So if a question ever asks you for you to draw the best Lewis structure, then what you need to go ahead and consider is the formal charge. And notice you always remove electrons from the more negative formally charged element and scooch them in. So what I'm going to do is go ahead and move these electrons down below. And the best resonance structure for sulfur dioxide satisfying the formal charge is going to look like this, where it's essentially oxygen with a double bond, oxygen to a double bond, and voila, looks just like this. And this Lewis structure is going to be your best one. This Lewis structure is going to be your best one for trying to satisfy the formal charge. All right, so let's go ahead and look at one last thing with this one in the middle here. I want you to try and identify the formal charge for the nitrogen and for the oxygen in the middle. I'll go ahead and give you guys a couple seconds to do so. What is the formal charge? About 5 seconds. I'm just seeing what kind of questions you guys have currently over at over here at the Fiveable site. I just want to say I'm so super stoked seeing you guys answering each other's questions. It's such a good way to study a little bit. So nicely done, nicely done. Cool. And I am actually really excited. I see a couple questions asking why can't I move the double bond from the other central oxygen? And this is why I had you guys answer this question here. So I'm going to go ahead and erase. It's going to do something annoying. Sorry, I don't know why it does that here. I'm going to erase this so I can talk about a couple of things. I'm also going to erase this here just so to look at this. You guys asked, why couldn't I remove the double bond? I hate that it does that, sorry. From this oxygen here. So I'll have the lone pair. Why couldn't I move these suckers over here? So that way my new one looks like this. I'm sorry it does that. I don't know why it does that. It's really annoying. Boom. So I moved those lone pairs over here. Well, based on my last drawing, the formal charge for every element in the structure was 0. In this situation, the formal charge for this oxygen over here is -1, and the formal charge for this oxygen here is +1. So the idea is that this Lewis structure satisfies the octet rule, but not the formal charge. Now, luckily, and this is a big luckily, for this particular question, if you drew this Lewis structure, since they did not ask for you to consider formal charge, this is a perfectly fine Lewis structure. But the other one that I drew for you was better. The other one that I drew for you was better because we're going to go back to it one last time, and I don't know why it's doing this. I'm so mad. I'm not really that mad. Boom, boom, boom. I have like 4 AP Chem tabs open now. This one is better. I don't know why I erased that. Boom. Because the formal charge for this oxygen is no longer -1, it's 0, and the formal charge for this one is no longer +1, but it's also 0. So the formal charge for everything is 0. And voila, voila. All right, I'm going to take a 5-second breather here, and I think you guys should all do the same. One of the things that I love to do with my students is have them walk and touch their front door, and I think you should totally do this as well. We've currently been doing this for an hour and a half, 90 minutes, so a full feature-length movie, which is crazy. I'm going to go touch my front door. I think you should too. Maybe grab a little drink, and I'm going to bring you back something, so I'll be right back. Look what I found. Look what I found. Look what I found. I found a Rufus. Found a Rufus. Rufus loves you guys. He says hi. He's the best. He was sleeping on the couch up front. Hi, baby. He was sleeping on the couch up front. He's like, I heard you're doing chemistry. I want to see your chemistry students. And so here he is. Upside down Rufus. You're heavy, dude. Mwah. Ugh. De-stressed dog. And now I woke him up too. Now I woke him up. That's Rufus. He's the chemistry mascot. He says hi. I hope you guys are all doing good so far. Hopefully you're getting all your wiggles out. What are you doing? All right. How are we doing here? We're doing great on time. I'm so excited. Let's see what kind of questions we have over in Fiveable land. In Discord as well. I'm glad some of the admin watching right now says hi to Rufus. I love it. That was the best message I got all day. Hi Rufus. His name's Rufus. He's so excited to say what's up to everyone. Rufus, why would you run during the AP Chem? He's so excited. He's actually always sleeping. He's always asleep. All right. You guys ready? So I'm sure there's a couple students out there where their front door is like a half mile away. So I was trying to give you a couple seconds to like run to the front door and run back, and you're probably like all out of breath. I mean, I had to carry this big lug of a dog all the way up front, and it's not really that far, but I'm not gonna lie, when I got back up front, I was like, okay, I'm out of breath. All right, let's go ahead and do a little bit more chemistry. Unit 2, we're pretty much finished with Unit 2. I have one quick little question that I wanted to share with you guys that I think you will really like, and that's going to be, well, hopefully really like. We'll find out here. And that's going to be, so really quickly, I want to point out one last time here. I want to point out one last time that SP2, that's all you had to write for this question here. And so what we're going to go ahead and talk about here is this question. I think this is a really great ionic bond type question. So as far as this goes, AP Chemistry does expect you to like recognize and write formulas for ionic compounds. We know that magnesium, being in the second column, has a charge of 2+. Same with strontium here. We have hydroxide. And so let's check out this question. It says, the energy required to separate the ions in MgOH2 crystal lattice into individual Mg and OH ions, as represented in the table below, is known as the lattice energy. As shown in the table, the lattice energy of SrOH2 is less than the lattice energy of MgOH2. Explain why in terms of the periodic properties and Coulomb's law. So once again, if you see the word in terms of this and this, it wants you to say or define something. So right off the bat, we have Coulomb's law. So I do want to point out that if you just kind of define Coulomb's law, hopefully you're doing that already in your head, you can quickly answer this particular question. So Coulomb's law says that opposite charges attract. And the opposite charges are more attracted to each other the closer they are. So as far as this goes, because we're comparing a +2 and a -1, these two ions are going to be pretty attracted to each other, and so is this Sr2+ and OH-1. But notice that the quantity or magnitude of the charge is the same. So that's not going to be what's affecting this lattice energy here. That's not going to be affecting the relative attractive force between these particles. And so if you go ahead and check out the answer here, we can see, well, the strontium ion is significantly larger. If you look at the periodic table, I'm going to switch away from this answer here really quick. Strontium is way further down on the periodic table here, and because of that, strontium is going to be larger. Remember, as you move down on the periodic table, the valence electrons occupy larger energy levels. So as far as this goes, strontium occupies greater, what am I trying to say here? Energy levels, and because of that, it is larger. And so when we go ahead and check this out, its valence electrons are in a further energy level or shell, and Coulomb's law states that opposite charges attract. So notice you get 1 point for comparing the sizes, and 1 point in terms of talking about the distances between the particles and referencing Coulomb's law, okay? Now, I notice, and I want to point out that all of these questions I pulled from the College Board questions that are available to you online, and I list the year and number, so this is coming from 2017, number 6, and there's some other good things for you to take away from that. And without further ado, let's talk about intermolecular forces. This is the biggest unit of the AP test. Roughly 20% of the AP test, is going to come from Unit 3. The rest of the units are about 10% of the AP test. So it seems to me that we want to be comfortable with intermolecular forces. Intermolecular forces is a big unit, but we can actually quite easily cover most of this. You do need to know the different intermolecular forces and the properties of solids, liquids, and gases. In this unit, we also cover solution chemistry, And the big takeaway from that is going to be molarity. And then last but not least, we're going to spend a few seconds talking about Beer's law and light in general, So let's go ahead and jump into this here. And I'm going to go ahead and pan down. We're going to make this document super long. And like I said, I'll make sure to go ahead and share this in Discord as well. So intermolecular forces, or IMFs, as they are lovingly called, IMF, intermolecular forces, are the forces of attraction between particles. And the forces of attraction between particles can be great, or they can be pretty weak. So intermolecular forces, once again, are the forces of attraction between particles. The strongest intermolecular force is going to be the hydrogen bond. And I want to point out that the hydrogen bond in the world of chemistry is not a chemical bond. It is not a chemical bond. And don't worry, I say this all the time. I wasn't there when they named this, so I have no idea why they decided, oh, let's call this thing that's not a chemical bond a bond. And you're like, dudes, really? Like, what were you thinking? So as far as the hydrogen bond goes, this is going to be the attractive force between two molecules that have a H bonded to F, O, or N. And there's a stupid way of memorizing it, but it always makes me laugh. Hydrogen bonding is fun. You get it? It's fun. So let's, for example, look at hydrogen fluoride, which is HF. The Lewis structure for hydrogen fluoride is as follows. It's basically a single bond between hydrogen and fluorine. And we know that fluorine is more electronegative than hydrogen because, and this came up earlier, I'll go ahead and close this out here. The electronegativity increases as you move up into the right, and this is for the electronegativity. Fluorine is the most electronegative element. Hydrogen, helium, neon, and argon are not included on this list because they do not form chemical bonds. Fluorine, being the most electronegative element, is going to be really good at taking electrons away from something like hydrogen. So because of this, this molecule here is actually pretty polar. It is going to have a very strong negative end and a very strong positive end. And what I've drawn here is the Greek letter delta. So it's delta, and this just means a partial positive or partial negative. This is still a molecule though. So my molecule here is kind of like this singular particle. If I bring another particle over, if I bring another HF molecule, it will automatically want to orient itself such that the negative end is near the positive end. And since fluorine is always going to be more electronegative than hydrogen, then the oppositely charged ends will go ahead and attract. The attractive force, once again, between one molecule and another is going to be called the hydrogen bond in this very specific situation, hydrogen bond. The next intermolecular force is called the dipole-dipole force. And the dipole-dipole force is the force of attraction felt between polar molecules. We'll use blue this time. Once again, it's the force of attraction between polar molecules. Rufus, by the way, for those of you in the Discord, he totally did run away. He literally was like, oh my God, he's talking about intermolecular forces. Peace out. He ran away. What I want to... Rufus, he's the best. We've had him for like a year and a half now. What I wanted to go ahead and show you for this example was hydrochloric acid or hydrogen chloride. Now, just like fluorine, chlorine is one of the more electronegative elements. So basically, you should know that nitrogen, oxygen, and chlorine are probably the four most electronegative elements. So when chlorine bonds with hydrogen, it's also going to essentially form the same exact thing that we see over here. It has a single bond between hydrogen and chlorine. And when we draw this molecule, this particle is going to have a slightly negative end and a slightly positive end. I do want to make it the same reddish colors though. So slightly negative and slightly positive. Boom, 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 and boom, and boom. So as far as this molecule goes, the positive end is going to orient itself near the negative end. And this oppositely charged like force of attraction between here is called an intermolecular force. And we call this a dipole-dipole force. Now I want you to look at these two drawings here. Analyze them. Study them. Make sure you're comfortable with what you're looking at. These two drawings are almost identical. The only reason that they are different is because I called this one a hydrogen bond and this one a dipole-dipole bond. And yeah, that's actually true. That's pretty much the only difference is what we call them. Hydrogen bonds tend to be significantly stronger though, because fluorine, oxygen, and nitrogen are very small. So these oppositely charged things can get very close to each other. These oppositely charged dipoles can get very close to each other. And so the hydrogen bond is significantly stronger than the dipole-dipole force. So voila, when we look at this here, we just call them different things, and that's because the dipole-dipole force is weaker than the hydrogen bond. But note that the mechanism between the attractive force is identical. Now, at the end of the day, you should be able to quickly recognize a hydrogen bond. And by the way, the answer to almost any biomolecule question, so if they're asking you about proteins or DNA base pairs or anything along those biomolecules, it's usually hydrogen bonding, but just be careful with that. The last thing that I want to talk about intermolecular forces is that non-polar molecules that don't have a positive or negative end, actually still have some sort of pretty strong force of attraction. And we call this the London dispersion force. We call this the London dispersion force. As far as this goes, this is really just going to be the force of attraction between non-polar particles, force of attraction between non-polar molecules. And a quick, short little list of something that is non-polar is going to be the diatomics, which is like the Brinkelhoff things, right? If you are literally listening to that and go, what did you just say? It's just a mnemonic that helps us memorize this, so Brinkelhoff. And the noble gases are a good one. Any hydrocarbon, which is something that contains only hydrogen and carbon. Essentially, the London dispersion force is the force of attraction between two things that generally are not charged. They don't have charged ends. And what this is due to, is the random motion of electrons. Due to the random motion of electrons. And so the more electrons you have, the more what you call polarizable you are. More electrons equals more polarizable. And so polarizability is directly related to the strength of the intermolecular force. So that's why something like wax, which contains like 20 carbons and 40 hydrogens, is a solid at room temperature because the strength of the intermolecular force. So let's go ahead and move on here and kind of show you what we should take away from the intermolecular forces. The stronger the intermolecular force, the stronger the intermolecular force, the ... higher the melting and boiling point, the higher the viscosity. And remember, viscosity is the resistance to flow. So something that has strong intermolecular forces is really viscous. Some good examples of viscous liquids are going to be like maple syrup or molasses, right? They don't flow very quickly. higher surface tension. And the last one always trips up students, so don't fall for this one. It's actually lower vapor pressure. So vapor pressure refers to the ability for a gas to evaporate. And the more gas particles evaporate, the higher the vapor pressure. So something that is really got weak intermolecular forces doesn't want to exist in the liquid phase. It much prefer to exist in the gas phase. It would like to evaporate. And because of this, you're going to have more particles in the gas phase, increasing the relative pressure that you are looking at. So let's go ahead and slowly transition this idea here from solids, from intermolecular forces, to the states of matter. So the different states of matter that I have are solids, liquids, and gases. So solids, liquids, and gases. Now, I do want to point out that we're going to spend a huge amount of time on gases compared to solids and liquids. What you should know about solids and liquids is really just this. Particles in a solid are densely packed. They're right next to each other. They do not flow. Particles do not flow. When I draw these, I almost always like to draw these kind of like particles right next to each other. And I draw like some shiver lines around them because we know that particles are always like moving based on the kinetic molecular theory, but solid particles are not flowing. Liquid particles are still quite densely packed, but they now have the ability to flow. And so when I draw my liquids here, I still draw them almost right next to each other. But the main difference is that I like to draw arrows indicating that these particles are moving around. That's pretty much the difference here. The difference between the density in a liquid and a density in a solid is pretty negligible. For example, there are a few instances where the liquid density of the substance is greater than the solid. For example, in liquid water is more dense than solid water, and that's why solid ice will float on water. And then the last one is gases here. Gases have like a huge distance between particles, We want to know, I'm going to go ahead and pan over here just a little bit. We want to know that particles of gases apply pressure due to collisions. Pressure is due to collisions. And essentially, all collisions are going to be elastic. And we also want to know that there's relatively low forces of attraction. So low intermolecular forces. As far as solids go, solids have the strongest or highest intermolecular force, strongest force of attraction between particles. The particles are so attracted to each other that they don't want to flow or move around one another. So as far as these three things go, once again, solids and liquids, just making sure you're comfortable with like the particle diagrams for them. Liquids, remember, can evaporate or boil. And the properties of liquids we have listed pretty much over here with the intermolecular forces. The stronger the intermolecular force, the higher the melting and boiling point, viscosity, surface tension, and vapor pressure. These bottom three here are all properties of liquids, but we're almost only going to study these qualitatively. For example, something that has a stronger intermolecular force, we know that it's going to have a higher viscosity, a higher surface tension, and a lower vapor pressure. So let's jump into our favorite part of intermolecular forces, which is all of the crazy properties of gases. So once again, gases are a massive part of Unit 3. We want to be comfortable with the ideal gas law. We want to be comfortable with the different relationships between the properties of solids, liquid, of gases, which would be pressure, volume, and the number of particles. And we want to understand how we observe or look at real gases in comparison to what are called ideal gases. So I kind of listed some of the properties of these ideal gases here. Ideal gases are considered to be infinitely small, which means that there are going to be massive distances between particles. We know that, once again, the gas particles are going to have elastic collisions. An elastic collision, FYI, is just going to be a collision that doesn't lose any energy. And then last but not least, an ideal gas is said to have no force of attraction or repulsion between them. And we need to understand that a real gas is going to be more or less ideal, meaning it follows these rules better or worse. So for example, real gases, and think about some examples of real gases. I can think of like carbon dioxide, oxygen gas, helium. These are all examples of real gases are going to behave more like a ideal gas at higher temperatures and lower pressures, are more ideal at high temperatures and lower pressures. So as far as this goes, the particles at higher temperatures are moving around faster. The particles are bouncing off of each other, and it kind of simulates this idea that their particles are very not attracted to each other. Low pressures means there's really, really large distances between the particles, and they're not colliding with each other as often. Remember, pressure is due to collisions. If you can kind of remember this, the relationships between the particles will kind of start sticking in your brain. Now, the big relationships for gases all extend from the ideal gas law. And the ideal gas law is as follows. The ideal gas law is going to be PV equals nRT. PV equals nRT. And on your equation sheet, they provide this for you. And they also actually give you a couple units for R. But I'm going to suggest that you only use 0.0821 atmospheres, liters per mole Kelvin. This, by the way, right over here tells you that all your units need to be in atmospheres, liters, moles, and Kelvin. And you only need to use this R value for PV equals nRT. Now, on the FRQ practice that I have in just a second, we will be looking at a PV equals nRT type question. So I won't do any of those right now, but I do want to show you that this equation actually helps us with all the other relationships. Now, there's not going to be a single question that says, like, what is Boyle's law, or what is Charles' law, or what is Avogadro's law? But they will ask you, what is the relationship between pressure and volume? What is the relationship between pressure and temperature, or volume and temperature? And if you know the ideal gas law, you can actually create any one of the relationships. For example, Boyle's law is going to show the direct relationship between pressure and volume. And that is going to be P1 V1 equals P2 V2. Notice that pressure and volume were on the same side. So when we show this inverse relationship, you multiply these two values in order to equal some other combination of these two values. The other good relationship would be, like, for example, Charles' law, which relates volume and temperature. In order to relate to these two, you just divide volume and temperatures of V1 over T1 is equal to V2 over T2. And we did that from, once again, just extending or looking at the ideal gas law. And one last good one is going to be Avogadro's law, which relates the volume and the moles. So that's going to be V1 over N1 is equal to V2 over N2. Now, this equation, once again, is given on the sheet, but these relationships are not. Last but not least, don't forget, temperature must be converted into Kelvin. Temperature in Celsius will equal, Kelvin will equal temperature in Celsius plus 273. So just remember that in order to do any ideal gas law question, any non-ideal gas law question, you must convert to Kelvin. You have to add 273. You have to add 273. So like I said, we'll come back to the ideal gas law and do an ideal gas law type question. But that's pretty much it, just being able to recognize all these relationships between pressure, volume, and number of moles. Now, the last kind of cool thing that we can relate to the intermolecular forces, which once again are all these properties and cool ideas and stuff like that, is solution chemistry. Now, solution chemistry is all that stuff regarding molarity. Molarity, remember, is the quantitative relationship for the concentration of a solution. So let's go ahead and look at, not molarity yet, let's go ahead and look at solubility. Now, there's actually two definitions for solubility. I'm going to go over first the qualitative definition and then the quantitative. The qualitative definition of solubility refers to the ability for something to dissolve into something else. Once again, the ability for something to dissolve, for a substance to dissolve, into a solvent. And for this, you need to take away this phrase, like dissolves like. Sorry about that. Like dissolves like. And what this tells us is that polar substances will dissolve polar substances, nonpolar substances will dissolve nonpolar substances. In general, something that is polar will not dissolve something else that is nonpolar. What I like to do for my students is provide them a list of polar substances and a list of nonpolar substances. But everything that we established earlier when we were talking about something that is polar and nonpolar with the electronegativity still applies to this list. So a couple things that are polar are going to be water, big time, acids and bases, sugars or alcohols. And if you took biology, if you took biology, you know that anything that ends in OSE, so glucose or fructose, is a sugar, and anything that ends in -ol, so methanol, ethanol, is an alcohol. And then don't forget polar substances. In this list, rather, we are going to include ionic compounds, but remember that ionic compounds are not polar, they are ionic. It's just that these things are really good at dissolving into water. And then a list of nonpolar things, nonpolar substances, are going to include some of those biological things like fats, oils, and waxes. This is, by the way, why oil doesn't mix with water, because oil is nonpolar and water is polar. Fats, oils, and waxes. This is going to include the diatomics once again. So these are the things that have London dispersion forces, the noble gases, any hydrocarbons, etc., etc., etc. So the qualitative definition of solubility basically allows for us to identify that water is really good at dissolving all these things here that have like intermolecular forces. So acids, bases, sugars, and alcohol all have hydrogen bonds and strong dipole-dipole forces, whereas fats, oils, waxes, and diatomics over here are all going to really only have London dispersion forces. So the London dispersion forces, that's pretty much it. And so they're really good at mixing with each other, but not over here on this list. Now, the quantitative definition of solubility is basically describing how much a solvent can dissolve into a solute. It's the maximum amount. And so quantitative is referring to, once again, the maximum amount of a solute that can dissolve in a solvent. So as far as this goes, we can increase or decrease the solubility of something by doing a couple of things. The easiest way to increase the solubility of a solid or liquid in another substance is usually increasing the temperature. So once again, and this doesn't always work, but by increasing the temperatures, you can sometimes increase the solubility. One may increase the solubility of a solid or liquid. Well, what's really interesting about this, solid or liquid, but what's really interesting about this is that the solubility for a substance, for a gas actually decreases when temperature goes up by increasing the temperature. One decreases the solubility of a gas. You guys ever had a warm soda before? And hopefully I'm not like making you feel like super grossed out by that. But warm sodas are generally pretty flat. And hopefully that kind of makes sense, right? If you have a warm soda, then the gas particles on the inside of the liquid are bouncing around more. And when they come into the contact with the surface, because they're gases, they can actually just leave the liquid. So once again, by increasing temperature, one will decrease the solubility of said gas. Now, in order to determine how concentrated a solution is, or maybe even what the maximum amount of solubility this thing can hold, we must look at the molarity. So molarity is pretty much the go-to calculation in this unit for trying to identify how concentrated a solution is. And molarity, which is big M, is going to be defined as the moles of the solute, divided by liters of the solution. So what I want you all to do, I'm gonna write you a quick question here. I want you to determine the molarity of a solution. What is the molarity of a solution that has, let's go ahead and say 75 grams of NaOH, sodium hydroxide, dissolved into a solution such that give you guys and me some room here. The solution's volume let's go ahead and say 215 milliliters. What is the molarity? Give me a couple seconds to think about this. I'm going to go get myself a little bit of water. Alrighty-o. So hopefully, cool. All right, so hopefully we could recognize here that the first thing you should do is determine the molar mass of NaOH. So the molar mass of NaOH, can be determined by summing up the molar mass of Na, O, and H. That's going to be 22.99 plus 16 plus 1.01. And we end up finding that this is 40 grams per mole. So the first thing we're going to go ahead and do is convert my 75 grams of NaOH to moles. 40 grams for every 1 mole. So 75 divided by 40 ends up getting us 1.875 mole NaOH. By dividing by the volume provided to me in liters, I can go ahead and find the molarity. So what I'm going to do is divide this here by 0.215 liters. 1.875 divided by 0.215 gets me a molarity of 8.72 molar. So my sodium hydroxide is going to be 8.72 molar. And I'm going to go ahead and stop sharing here for a minute here. And I want to go ahead and kind of switch gears because I want you guys to check out a couple of free response questions. So once again, kind of now that we're back here on me, just kind of shake it out, twist your head around. I'll maybe make you guys do a couple of jumping jacks here in a second. But what I want to go ahead and quickly check out is what a cool FRQ question related to Unit 3 would be like. Okay, so I'm going to give you a couple of seconds to check out this question here and try it out on your own. And once we go ahead and do that, we will talk about light and Beer's law. And once we talk about light and Beer's law, we can then move on to Unit 4. So I'm going to pull up, there is the chemical reactions. I promise I'll talk about this in a second here. But let's go ahead and do part A, part I. One FRQ tip, by the way, that I would love to tell you guys is this. Whenever I get to the FRQs and the questions, I almost always like to just read the parts that they ask me. So it says, how many moles of Cl2 are in the container? And then it comes back even here and says the chlorine gas Cl2 is initially present in the container at a pressure of 0.4. So kind of when I do this, by reading this first, I can kind of come back up to the top here and see if I can answer that FRQ. If I do part AI and part B, or excuse me, when I finish part AI, I want you guys to also check out part B with this down below, which is the Maxwell-Boltzmann distribution. So I'm going to give you guys a few seconds to check this out, and I will be right back. I'm going to take a little breather here. I'm gonna give you guys about 2 more minutes. All right. So let's go ahead and just stop sharing here really quick. What we're going to go ahead and do is look at the FRQ answer to part A, part I, A part I, however you want to go ahead and say that. And for this particular question, it's going to be applying the ideal gas law. Now, part II of A is a stoichiometry question. We will come back to this when we do chemical reactions in like 2 seconds. And then the last 2 questions, part B, are going to be looking at the Maxwell distribution, which is listed down below. And I really just have 2 quick things that I want to show you regarding that. So hopefully, if you went ahead and answered these questions here, you could see first that you solve PV equals nRT for the value of n. When you do this, you end up finding that the number of moles of chlorine gas is 0.31. Give yourself a pat on the back if you went ahead and did that one correctly. Now, I want to remind you that the next answer I'm going to go ahead and show you here is for part II of A, and I'm just going to quickly skip over this one for right now. We'll come back to it. Next, this question says, explain how the higher temperature affects the collisions between the reactant molecules so that the reaction occurs at an observable rate at 120 degrees Celsius. Now, notice I didn't read part B here. Once again, this tip here that I'm trying to do is give you a little bit of extra time during the FRQ. Now, if you're reading through this and you're saying, okay, temperature affects the collisions, well, I know that at higher temperatures, the particles move faster, and therefore, if they're moving faster, they're probably going to have greater collisions. You're pretty much halfway there with that particular answer. Notice that when you get to this answer here, it says this. At the higher temperature, the particles have a greater average kinetic energy than the lower temperature. Thus, there are more collisions with sufficient energy to overcome the activation energy. Do you guys remember my quick tip for this, by the way, or tip before? Make sure you actually answer the question. If you didn't refer to the number of collisions increasing, you probably wouldn't get the full points, even if you said at higher temperatures, the kinetic energy is greater, because the question specifically asked, how does this affect the collisions? Make sure you actually answer these questions. The last question that I want to go ahead and look at here is part B, part II. The graph below shows a distribution for the collision energies of reactant molecules. Draw the second curve on the graph that shows the distribution for the collision energies of the reactant molecules at 30 degrees Celsius. And what I want to show you here is actually, I'm going to draw a couple things on this graph down below that I think are going to be super helpful for you. There are basically 2 situations that we can be looking at. One is going to be higher up and then flatten out sooner. And the other situation is going to go out further and have a peak that's lower and then kind of slowly flatten out. So basically, these are my two situations here. These are my two situations, and I probably didn't choose the best colors because you'll see in a second here. The graph that is further to the left with a higher peak is always going to be the one at a lower temperature. I'll switch lower temperature. This could also be referring to the particle that is heavier. Okay, the heavier particle will always be moving relatively more slowly. The peak that is further to the right but shorter will always be referring to a higher temperature and always be referring to my lighter particle. Now, notice in the context of this question, it's referring to temperatures. We're wanting to draw the 30-degree graph versus the 120. So we're looking at lower temperature or higher temperature. So hopefully if you drew the red graph, you're good to go. But if they were referring to the mass of the particle, then you'd be looking at the part down below it. But these are always the answers. It's either to the left and higher up or further to the right and lower down. So let's go ahead and check out and see if we got the answer correct for this. And wouldn't you know it, the graph is going to be further to the left with the peak that is higher. And you're actually available to have 2 points. 1 point is earned for a curve that has a peak above and to the left of the curve. 1 point is earned for a curve that is below the given curve in the region beyond the activation energy. So we wanted to have this region kind of dip down low because what it was talking about is not having sufficient energy in order for our reaction to occur, not in order for our reaction to not occur. So I'm going to go ahead and pause sharing here. And what I want to go ahead and do is share the last little piece about Unit 3, which is going to be light. And it's so weird that they put it in this unit, but what they're doing is making a connection to Beer's law. So I'll go ahead and show you kind of what's going on with Beer's law at the very end of this little unit here. But first, I want to go ahead and discuss light. Boom, boom, and boom. Voila. So as far as light goes, it's kind of funny that we study light in chemistry because chemistry, right, is the study of matter. Light is not matter, but light does affect matter. Light does funny, interesting, kind of cool things to matter, and we want to be comfortable with that. So basically, the two things that you should take away from light are the equations, which are C equals lambda nu and E equals h nu. Lambda refers to the wavelength, and wavelength describes the distance between particles, the distance between the peak or the trough, and its units are often going to be in meters. But you should know that there are 10 to the 9th nanometers in 1 meter. And the reason I'm giving you this is because the visible region of light is in the nanometer region. And obviously, us being humans, we are looking at and viewing the visible region in space. So we want to be comfortable with that. The letter nu refers to the frequency, and this refers to the number of cycles per second. The units for this are oftentimes in hertz, but sometimes we'll see, I don't want to write that. Sometimes we'll see seconds raised to the negative first, and basically you're counting 1, 2, 3, 4, 5 times per second, or in terms of light, a million times per second, or a billion, or a trillion. It's usually quite a large number. E refers to the energy of light, and H and C are both constant values. We'll write C here. C is the speed of light at 3 times 10 to the 8th meters per second. And H is Planck's constant, which is 6.626 times 10 to the negative 34th joules seconds. So as far as these particular questions go, what they'll often do is give you a frequency, a wavelength, or an energy, and then ask you to calculate one of those other values. I do want you guys to be careful, though. Sometimes they give it to you in joules per mole, energy in joules per mole, and these equations are only ever for a single photon. So don't forget that 1 mole is equal to 6.02 times 10 to the 23rd photons, if we're talking about light particles here. It is super important that you recognize that this conversion factor may come up. It may be appropriate for you to know this. Otherwise, though, what I wanted to quickly show you guys was a really fun simulation. This simulation I use all the time with my students. And one of the things that we can kind of go ahead and do is study how light is affected by matter. And so what I'm gonna go ahead and do is actually jump over here to my Beer's Law simulation, and we're gonna look at drink mix. Don't worry, we'll actually use a chemical here in just a second. But what's cool about Beer's Law is something that you've probably all been comfortable with and seen many times in your life. When I was a kid, my mom used to always dilute my drink mix because it was too sugary and I was like super high strung. And so she would always make the concentration of the drink mix a lot lower by adding water. She would dilute it. And so watch what happens here. So a couple things I want you to notice. The drink mix is bright red here. The drink mix is going to be bright red. And the absorbance is this value here, which measures how much light is captured by this drink mix. So what I'm going to do is slowly lower the concentration. And the first question I want you to answer is, what happens to the color of the solution? So here we go. Slowly and then eventually it becomes clear. This totally makes sense. As the concentration increases in the solution gets darker. There are more particles floating around, and the particles, as they increase, it becomes darker. The solution becomes more difficult to see through until eventually you get to the highest concentration in this situation, which is roughly 400 millimolar, 400 millimolar. So we'll go back to right here, right in the middle. And what we can see is that as I increase the concentration, the absorbance increases as well. And that's what Beer's Law is. Beer's Law is the direct relationship between absorbance A and concentration C. But there are a couple other factors that actually go into this. The other factors are, first, how wide this cuvette is. So this device here is called the cuvette. And the cuvette is basically a tiny little piece of glassware that you put a sample of your solution in. So what that is measuring is B. And notice, watch what happens here as I increase this here. As I increase, the absorbance increases it. As I decrease the absorbance, the cuvette length, it decreases. And I didn't realize I was drawing on that. That's kind of funny. So once again, as you go right, as you go right, increasing the length of the cuvette, the absorbance increases because you're increasing the amount of solution it has to pass through. We'll say 95% of the time, the path length is 1 centimeter. I do want to point out, I've seen on FRQs and multiple choice this value changing. That's why I said 95% of the time, but most of the time the cuvette length is 1 centimeter. The next thing that it depends on is actually the solution itself, and this value here is called the absorptivity constant. Epsilon is the absorptivity constant. It's just a constant that relates the absorbance, the path length, and C, the concentration. So at the end of the day, let's see if we can get roughly. I can move my centimeter over here, my stick. Boom, voila. Essentially, Beer's Law is doing this. It's tracking the absorbance and the concentration, because as the concentration, as I showed you earlier, increases, notice that the absorbance increases. As the concentration decreases, the absorbance decreases. And what's really rad about this process is that if I plot the absorbance versus concentration, you actually get a straight line. So basically, at the end of the day, you can use this equation here, and you should try to use it, especially if they're giving you specifically the path length or the molar absorptivity constant. But if you're really lucky, they'll give you a pretty straightforward question. Cool, thank you. They'll give you a pretty straightforward question where you're like, oh, my absorptivity was like 0.5. What is the concentration? And all you have to go is like, bloop, 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 and then you're good to go. And it's like, this is like 0.27. I don't know, making up the numbers down below here. So that's pretty much what Boyle's law is. And I actually have a fun little question at the end of our session today, part of our games that goes over a little bit of Beer's law in more detail. But that's the main takeaway for Beer's law. And ladies and gentlemen, that is Unit 3. Unit 3 is a biggie, but what I really enjoy about Unit 3 is that you really are just focusing on, how do I want to put this? Unit 3, you're really just focusing on the intermolecular forces, so hydrogen bonds, London dispersion forces, dipole, the gas law, PV equals nRT, solutions, which is the molarity equation, and the light equations, which we went over just there. Now, the last little thing I wanted to show you regarding what we just talked about was that last question here. Looking at, the last thing that I wanted to go ahead and do is talk about Unit 4 in a little bit more detail. So hopefully, if you are following along and kind of asking great questions in chat, in the Q&A section down below, I want you to keep doing that because your peers are doing great jobs answering each other's questions. I love it. Keep doing it. It is helping you guys get to that. So keep answering your peers' questions in the Q&A section on the Fiveable. I'll keep kind of perusing it every time I need a quick little break. And don't forget, y'all, you can upvote or downvote things. And the way I'm organizing it is by looking at the most upvoted questions. So if you see a question that you want me to answer, I need it to be upvoted. So that's just going to make sure you actually do that there. Unit 4 is the chemical reactions. What's super rad about this unit is it's actually pretty quick. What I mean by this is that as long as you understand the basics of stoichiometry, as long as you understand the basics of precipitation, acid-base, redox reactions, you're pretty much good to go. We will go into more detail with acids and bases and redox when we get to Unit 8 and 9 respectively. And as I'm sure you are all freaking out about, and justifiably so, we'll go into a lot of detail discussing those titrations, all right? So, what is a chemical reaction? One of the interesting things that comes up with this unit is they actually do expect you to know the difference between a chemical reaction and a physical process. And it's actually really straightforward. A chemical reaction is going to be any situation where the bonds form or break. You're forming new bonds or you're breaking new bonds. The atoms rearrange. You have to have this in order for a chemical reaction to occur. In order to do a physical process, on the other hand, the matter changes. We'll use purple for this. The matter changes, but no new bonds form. So for this, oftentimes, state changes or phase changes are the most common examples, there we go, of physical processes. Water boiling, carbon dioxide subliming or dry ice subliming are both examples of physical processes. Other than that, everything in this unit is going to be a chemical reaction. So the first thing I wanted to go ahead and do is remind you just briefly, what is stoichiometry and what do you need to know from this? Well, in order to do well with stoichiometry, you need to be comfortable with the mole ratio. And the mole ratio is basically relating moles of one substance, of one chemical, to another. So mole A to mole B. And in order to do this, we use, once again, the mole ratio, which comes from the balanced chemical equation. So if I were to look at, for example, something along the lines of the combustion of methane, I will get that down one of these days. Pen versus pan. They need to have the pan button over here. I think that's what's going on here. We have CH4 reacting with 2O2, making 2H2O and CO2. So this is the combustion of methane. And what's essentially happening here, if I want to relate any substance to any other substance here, we use the mole ratio. And the way we do that is by looking at the coefficients from the balanced chemical equation. The coefficient for CH4 is 1, coefficient for O2 is 2, coefficient for H2O is 2, and the coefficient for CO2 is 1. So this reacts in a 1 to 2 to 2 to 1 ratio. What essentially that tells us is that for every 1 mole of CH4 that will react, it will react with 2 moles of O2. It will produce 2 moles of H2O, and it will produce 1 mole of CO2. So in a really kind of simple way of looking at this, if I had 27 mole of CH4, how many moles of H2O could I produce? Well, in a simple world, we know that 1 mole of CH4 will produce 2 mole of H2O. And in a 1 to 2 ratio, this is going to produce 54 mole of H2O. Now, as far as this goes, this is the type of multiple choice question you could expect to see on the quantitative side of things. It could get more challenging than this, but not by very much. Being able to do some simple multiplication and division is expected for you tomorrow. At the end of the day, write out everything that you can. Make sure you write out all your work, because the more work you show, the more you'll be able to kind of justify what that math looks like. And don't forget, y'all, when you're doing multiple choice questions, you don't have to get that final answer. If you plug this in and you're like, oh, 20, say you didn't even write this over here, you're like 27 times 2 is 54, and 54 is letter A, then just jump on that and move on. Don't waste too much time writing out answers and stuff like that. Now, to practice stoichiometry, what I would love to go over and look at is a limiting reactant type problem. Now remember, limiting reactants are going to be when one of the reactants runs out. Limiting reactant problems are super important on the AP test. They love asking about this. This essentially halts the chemical reaction, and however much product you made at that point is however much product you've made. So limiting reactant, once again, is going to be when one of the reactants runs out. When one of the reactants runs out. And what I want to show you is actually one of the simplest ways to do a limiting reactant type problem. So let's say we have the chemical reaction 2SO2 reacting with O2 to make 2SO3. As far as this reaction goes, I find out that there are 25 grams of SO2, and let's go ahead and say 43 grams of O2. So the way I set this up, let's actually write it like this: 25 grams of SO2 and 43 grams of O2. The way I've set this up is so that we can do the quick method for limiting reactants. The quick method is this. The first thing you want to do is convert both of these values to moles. So 25 grams of SO2, the molar mass of SO2 is going to be 64 grams per mole. Once again, we find the molar mass by looking at the periodic table. There were 2 oxygens, so 32, and 1 sulfur, which is also 32, so 64. And the molar mass of 2 oxygen atoms is 32 grams per mole. Each of these values is going to be 25 divided by 64, 0.39 mole SO2. And 43 divided by 32 is going to be 1.34 mole O2. The next thing you want to go ahead and do here is divide by the coefficients from the balanced chemical reaction. We see that SO2 has a coefficient of 2, O2 has a coefficient of 1, And whichever one of these values is smaller, is your limiting reactant. So we can see here that my limiting reactant is going to be SO2. And the reason it's going to be SO2 is because when I do this quick calculation here, this number is smaller. So SO2 is the limiting reactant. Now, I do want to point out that these numbers I calculated here are kind of like garbage numbers. We're not going to use these for any calculation. So I sometimes after I do this, I write my statement here and then just like cross them out so I don't confuse myself. 0.39 mole and 1.34 mole are still good numbers, and you can use those for any subsequent calculation down the road. All right, so now let's go ahead and discuss the different types of chemical reactions. And there are three big types. We have precipitation reactions, redox reactions, and acid-base. Precipitation reactions are actually pretty much the most straightforward in this series. So precipitation. Precipitation reactions go ahead and produce a solid. These are going to be a reaction, Rx, where a solid is produced. So a good example for this would be something along the lines of silver nitrate, which is aqueous in water, reacting with potassium chloride, which is also aqueous, produces potassium nitrate and silver chloride, AgCl, solid. Now, you actually do have to be able to recognize which one of these is the precipitate. The easy way is to just identify whichever one has the solid listed next to it. But in this situation, we also want to know that certain ions will always be soluble in water. And the mnemonic for this is SNAP. Oh, snap. Anytime we have sodium, which is Na+, nitrate, which is NO3 minus, ammonium, which is NH4 plus, and potassium, which is K plus, these are always water soluble, always aqueous, AQ. So we can see that KNO3 has both K and NO3, so it's definitely going to be aqueous. AgCl had neither. And that's how I'm able to recognize that AgCl is the precipitate in this situation. The next type of chemical reaction that we want to go ahead and look at is the redox reaction. Redox reactions are going to be any chemical reaction in which an electron is transferred. Redox is also, by the way, short for oxidation reduction. Any reaction where electrons are transferred. And you know that you have a redox reaction, transferred. You know that you have a redox reaction when the oxidation state changes. So that's what essentially we're looking for here. We're looking for a oxidation state change, or a change, not a charge, a change in the oxidation number. And the easiest way you can do that is by making sure you're comfortable with calculating or determining what the oxidation number is. Now, the oxidation number is quite literally just a value assigned to help us balance redox reactions. And we'll look at balancing redox reactions at the end of our session today. But oxidation numbers can easily be determined, oxidation states, using the following rules. Number one, the oxidation state for an element, the oxidation state. And I'm just going to, from here on out, say 0 pound. So oxidation number for an element is 0. So for example, sodium which is solid, would be 0. Oxygen gas would be 0. Ozone would also be 0. Basically, anytime you have an element, that's going to be 0. Next, the charge of the ion, if it is an ion, is going to equal the oxidation state. So 2, the charge of a monatomic ion is equal to the charge. So as far as this goes, if we're looking at something like, let's do magnesium chloride, which is MgCl2. Well, the charge for magnesium is 2 plus, so that would be 2 plus, and for chlorine, it's going to be 1 minus. Now, what's really cool about oxidation states is that we can do redox reactions for molecules as well. And when we go ahead and look at these, the oxidation state for a couple elements will pretty much always be the same. So for example, oxygen is usually 2 minus, while hydrogen is 1 plus. And this is when they are in molecules. So for example, something like carbon dioxide, CO2, the oxygen here is going to be 2 minus. And if I were to look at CH4, then the hydrogen is going to be 1 plus, 1 plus. And so as far as this goes, this kind of leads me to my last quick little redox rule, which is that the oxidation state must add to the charge. The oxidation state or number must add to the overall charge. And when we go ahead and look at the overall charge for carbon dioxide or CH4, these examples are neutral. So in this situation, because there were 2 oxygens, oxygen, right, has a negative oxidation state of -2. That must mean that carbon here is going to have an oxidation state of 4 plus. But there are 4 hydrogens in this example, so carbon in this situation would be 4 minus. So yeah, the oxidation state for substances may change, they may change. And so you just kind of need to look out for situations like that. All right, what I'm going to go ahead and do is this. You guys have been totally crushing it. You're doing such a good job at doing and kind of discussing chemistry with me. So what I'm going to go ahead and do is invite you to look at this next FRQ and try it out. So I'm going to go ahead and skip through a couple things here. Really quickly, I do want to point out that we did skip over at part AII. So I'm going to give you a few minutes to check that out. If you've already done it, good for you. I'm going to give you, like, let's say 2 minutes. And for this, you may need to find your answer for part AI, which I can remind you really quick is 0.31. So I want you guys to go ahead and try to determine how many grams of carbon disulfide are needed to react completely with Cl2. And you need this balanced chemical reaction here. So I'm going to give you 1 minute to try that out, literally just a minute, and then I'm going to go ahead and do another free response question for you to check out. All right, so hopefully for this particular problem, hello, I'm back. Sorry, sometimes I do that with my students when I do like online learning. I'm like, go ahead and try this problem. And then I don't talk for like 30 seconds or 60 seconds. And then I come back and like start saying words and they go, oh, Mr. Winter, you scared us. And I'm like, I'm sorry, I didn't mean to scare. It's a whole thing. It's a whole thing. So hopefully with this particular problem, all you really needed to do was spend a few seconds determining the molar mass of CS2. And there was a 1:3 ratio between chlorine and cesium. So if you got 7.9 grams, you are good to go. Notice that for any part of this, they oftentimes will give you partial points for mole ratio and stuff like that. So 1:3 ratio there. I'm going to let you guys try one more question here. And that's just identifying which species is reduced in the titration reaction above. Notice that once again, for a lot of these questions, I often will not read the question until I'm prompted to. I love reading the part A, part B, part C before reading the big paragraph. Because for this, I can just read the question and then answer by looking at the balanced chemical equation. I didn't have to waste my time reading the paragraph. Eventually, you will have to read the paragraph, but not for this particular scenario. All right. See, that was a more calming voice, right? If I kind of come back and like warm you up to it. I just wanted to say, first off, way to go, Discord crew, and way to go, the Fiveable Questions crew. Thank you so much for doing your best to help answer questions of your peers and kind of help me manage some of these things here. That's what I love working about this community, is that you guys are all willing to help each other. And by the way, helping each other helps you study for this test. So keep it up. Keep it up. So as far as this goes, let's see if we can identify which species was reduced in this particular redox reaction. So as far as reductions and oxidations go, I didn't quite discuss what that meant. I was just kind of seeing if you guys could kind of get that away with yourselves. I know I'm being mean. I know, I'm sorry. But alas, the AP test is tomorrow. Don't forget our lovely phrase, oil rig. Oil rig basically helps us identify which substance is being oxidized and which substance is being reduced. Oil stands for oxidation is losing electrons. So oxidation is losing. And reduction is gain electrons. So whenever I lose electrons, I become more positive, and whenever I gain electrons, I become more negative. So basically, my goal here is to find the species that gained electrons. I want to find the substance that got more negative. And so by doing this, I'm going to go ahead and close this out here. I see that MnO4 is reduced to Mn2+, because the oxidation number for manganese changed from +7 to +2. Once again, I can kind of show you what's happening here. If oxygen is always -2, then manganese must have an oxidation of +7. There are 4 oxygen atoms here for a total net charge of -8, but there is a -1 charge on the molecule, so it's 7. So notice how it went from +7 to +2, which means that it got more negative. So manganese is the species that is reduced in this chemical reaction. So oil rig, yeah, I know, I'm sorry, I kind of left that away from you guys, but don't you forget it. And what I want to do, what I kind of want to end with, not end with, guys, we still got 2 hours. I want to play you a little bit of a song just to kind of groove out for a second. We've been here for an hour, so if you want to dance a little bit, I'm just gonna kind of like chill here, trying to like watch my voice a little bit. It's still like really nice in Santa Cruz today. I'm like looking out my window. I have this beautiful palm tree in the back, and what's so funny is there's always squirrels fighting. So if any of you guys are into Wolfpack, I love this crew, and the song is called 1612. So I hope you enjoy it.
It's a sense what you need to tell it. Sometimes I write a little song so you don't forget it. Sometimes I write a little song to remember the lyrics. I go 16, 12. That's a code to my heart. I go 1, 6, 1, 2. Star Aquarium for Taurus. A strike on the box. Ooh, for focus. Pretty flat Donnie Hathaway. Frank Sinatra. 16, 12. That's close to my heart. I go 1, 6, 1, 2. Ooh, star. 16, 12. That's close to my heart. I go 1, 6, 1, 2. Star. No. Peace of mind, a friend of mine. Whoa, 16, 12.
You can stand up a little bit.
I go 1, 2, 3
hours of chemistry.
I go 16, 16, 12. If it goes to my heart, 1, 6, 1, 2, ooh, star. I go 16, 12. Is a gold to my heart. I go 1, 6, 1, 6, 1, 6, 1, 6, 1, 2. Oh, 16, 12. Is a gold to my heart. I go 1, 6, 1, 6, 1, 6, 1, 6, 1, 6, 1, 6. I go 16, 12. It's gold to my heart. I go 1, 6, 1, 2. Hey, hey, hey. I go 12 is the key, is the key, is the key, is the key. 12 is the gold to my heart. You better never, ever forget it. You better never, ever forget it. Never, never forget it.
I know I'm still alive, but every time I listen to that song, I get so into it. I don't know about you guys, but like, right? It is so groovy. It's just, you're like, oh, so good. I needed that. I don't know about you guys, but I was starting to get a little like, oh, I am so ready. Like, I needed that. That really pumped me up. That really pumped me up. I'm so stoked. That was a good idea. All right, guys. So what we've done so far is 4 units. Luckily, units 5 and 6 are actually pretty mellow, quick units, and there's really just a couple of things that you need to be comfortable with, know comfortably on the AP test. And if you got those things down, you are crushing it. You are doing so good. All right. So let's go ahead and jump into unit 5 here. And what we're going to do is really just make sure that, once again, you know the problem types that will come up in Unit 5. So Unit 5 is kinetics, how fast chemical reactions will occur. And the biggest takeaway, in my opinion, for this is the collision model. Now, don't get me wrong, though. There are going to be rate laws and integrated rate laws. And the practice FRQ that we'll check out today deals with mechanisms. So let's jump into it. Let's go back to our whiteboard over here. And what I've decided to do is kind of talk about acid-base chemistry in a little bit more detail and the acid-base reactions when we get to Unit 8, which is, guess what, acids and bases. So let's go ahead and pan down here and talk first about the collision model. The collision model is the big important thing from this unit, meaning that when a chemical reaction occurs, it can either happen more quickly or more slowly, and it's all about how those particles collide with each other. So the collision model, once again, basically says that a reaction will only occur if the particles collide with the right energy and in the correct orientation. There we go. And the basis of this will help us understand how fast a chemical reaction will occur. Because if the particles collide but with not the right amount of energy, they will not react. If the particles collide but if they don't do so in the right orientation, they will not react. So the collision model really helps us understand in more detail how fast a chemical reaction occurs. We can also graphically represent, we can also graphically represent how fast a chemical reaction occurs using a reaction profile diagram or a reaction coordinate diagram. The reaction coordinate diagram always plots the potential energy versus the reaction progress, the progress of the reaction on the x-axis. And they always look like the following. We either have reactants higher than products, or the products higher than the reactants. And in this situation, notice how they always overcome some sort of barrier. Now the barrier, taking the difference between the top of the peak and the reactants, is the activation energy. Once again, the activation energy, which is in green there. Activation energy is the minimum amount of energy required to initiate a chemical reaction. So we need to overcome this barrier here in order to start this chemical reaction. And notice here on the right-hand side, we need to overcome a massive barrier in order to initiate this reaction. So based on just like the graphs, if these were relatively to scale, saying like the top of this peak is relatively the same as the top of this, then the graph on the right will take a lot more time than the one on the left, because the peak is a lot higher. The higher the peak is, the longer the chemical reaction will take. The difference between the reactants and the products is going to be the enthalpy, or delta H. We'll talk about delta H here in just a second when we get to thermochemistry. So once again, the difference between the reactants and products is the delta H. And once again, the green here is what we call the activation energy. Now, these will answer most of your qualitative type questions from Unit 5. If they're talking about a chemical reaction not occurring in a reasonable rate, the biggest reason is usually that the particles don't have enough energy to overcome that barrier, overcome the activation energy. And one of the easiest ways to speed up a reaction, and this is true for all of them, is by heating it up. By heating it up, you will increase the speed of the reaction because you're basically increasing the amount of collisions between particles. Now, the main problem type that you will see in Unit 5 is determining the rate law. Rate law refers specifically rate law refers specifically, excuse me, tongue-tied here, to relating the concentration to the rate of the reaction. So rate laws show how concentration and rate are related. Concentration is related to rate. And they will pretty much always come in this form. Rate is equal to lowercase k times the concentration of one of the reactants or products raised to some power, so like x, times the concentration of one of the other reactants to raise to some different power y. X and y can pretty much only ever be 0, 1, or 2, but I do want to point out that they can absolutely be other numbers, and they don't even have to be whole numbers. But like, this is one of those ones where 95% of the time, it will be 0, 1, or 2. A zero-order reaction basically tells us that the concentration of that reactant does not affect the rate of the reaction. A order of 1, an exponent of 1, tells us that the concentration of the reactant will affect the rate in exactly the same way. And a exponent of 2 basically will tell us that the rate will change a square to how the rate, the concentration of that substance changes. Now, what's really kind of interesting about these is that you can only ever study them experimentally. So let's go ahead and look at the data they will give for this. What they'll always do is say something like trial number 1, 2, 3. They'll say the concentration of A, the concentration of B, maybe they'll even throw in the concentration of C. And then what they'll do is they'll tell you the rate. Let's go ahead and also make this 4 here. I'm going to show you all situations. And what they'll do is they'll end up doubling or tripling some of the values here. So for example, A could be 0.1, B could be 0.1, and C could be 0.1. I'm going to make my life a little bit easy here. And the rate of the reaction is something along the lines of, I don't know, let's say like 2.2 times 10 to the negative 3. So in the first situation, let's go ahead and like double the concentration of 1. Let's go ahead and change it to 0.2. I'm going to keep the concentration of B and C the same though, because remember, in good scientific controlled experiments, I only change one factor of the experiment at a time. So I'm just going to be changing the concentration of A while keeping B and C the same. And what I notice is that when I double A, the rate of the reaction doesn't change. What this essentially tells us is that the order of the reaction for A, or with respect to A, is 0. So the concentration of A will be raised to the 0th power, because as this doubled, this did not change. This was multiplied by 1. It did not change. All right, in scenario number 2, let's go ahead and double B now. So B is doubling. Well, by doing this, let's go ahead and say that it also doubled the rate of the reaction. Well, what this tells us is by doubling the concentration of B, and with the rate changing, we go ahead and see that the rate changes in the exact same way that the concentration of B changes. So the order of the reaction with respect to B will be to the 1st power. And then last but not least, let's go ahead and double the concentration for C. And once again, this is a completely theoretical situation here. And from C down below, we went ahead and doubled it. And in this situation, let's do 2.22 times 4. Yeah, that's right. The rate will be 8.8 times 10 to the negative 3. The rate quadrupled. Ooh, that's not a 4, that's a 2. The rate quadrupled. And so what's essentially happening here is that the change of the rate is square of how the concentration changed. So this would be to the order of, I need to scooch you down just a little bit, to the order of 2, or squared. So essentially, when you get data like what we have down below, I'm actually going to rewrite it down below so you can see it here. And then the way you answer it is by observing. The way you answer it is by observing how changing the concentration of A, B, or C will affect the rate. And my final rate law will equal K times the concentration of A raised to the 0 power times B raised to the 1st power times C raised to the 2nd power. And once again, this is completely based on the data. This is completely based on the data. So as far as this goes, now that I have this, a next question that could come up is to calculate the value of K. And really, these are just experimental values. How do I want to say it? It's not experimental values. Experimented. Oh, wow. I am totally tripping up on my words right now. These are basically algebraic expressions. Sorry about that. So if I want to go ahead and determine the value of K, then all I have to do is choose literally any one of these experiments. I'm going to choose experiment number 4 here and just plug those values in to my expression. So I know that for experiment 4, the rate was 8.8 times 10 to the negative 3. Usually it's like molar per second. K is what we're looking for. A was 0.1 raised to the 0 power. B was 0.1 raised to the 1 power. And C was 0.2 squared. By solving this expression, we get lowercase k, the rate constant, is going to be 8.8 times 10 raised to the negative 3 divided by 0.1 divided by 0.2 squared. And we actually get, ooh, interesting, 2.2 here. And I can actually pretty confidently answer that the units for the rate constant here will be 1 over molar squared times second. And you're probably going, wait, how in the world did you do that? And there's actually a really easy trick for determining the units for K. And by the way, they do expect you to know the units for K. Depending on the overall order of the reaction, the units for K change. And there's a quick little chart / thing I want you to notice here. So when we are doing the units for K, all you need to identify is the overall order of the reaction. And the overall order is found by summing up the exponents here. So in this case, the overall order would be 3. And based on this chart here, you can determine what that's going to be. So order and then units for K. So 0, 1, 2, 3. We'll go all the way down to 3. So the units for K, if it's 0th order, is going to be molar per second. For first order, it's going to be per second. For second order, it's going to be 1 molar second. And then 1 over molar squared second. Do you guys see what that pattern is? Do you see what that pattern is? This pattern, every time we go down in order, we divide by m. So for third order, it's just 1 over molar squared second. So if you were to do like 14th order, let's say we have a chemical reaction where the overall order is 14th, this is just going to be 1 over molar to the 13th times second. All right. So once again, that is how we define the rate laws. The rate laws are how we look at the overall, how the concentration, affects the rate of the reaction. Up next, we have the integrated rate laws. And as far as the integrated rate laws go, the integrated rate laws show us how time affects concentration. So the integrated rate laws show us once again how time affects concentration. And the integrated rate law, just like the regular rate laws, depend on the order of the reaction. Time affects concentration. So there are 3 integrated rate laws that you need to know, and the 3 integrated rate laws are 0th, 1st, and 2nd, but luckily they are provided to you on the AP reference. What's not provided is which one relates to the overall order of the reaction. So I'll actually jump over here to the reference sheet. Once again, don't let tomorrow morning be the first time you're looking at this reference sheet. And if you scroll down here to kinetics, you see these three equations here. These three equations are the integrated rate laws. And notice, once again, they are provided to you, but there's no information about them given. Luckily, they are written in the order of increasing order. So for this is going to be the 0th order integrated rate law. This is going to be the 1st order integrated rate law. And this is going to be the 2nd order integrated rate law. These rate laws are super helpful for determining how much of a substance you have after a given amount of time, as long as you know the order of the reaction. Now I'm going to go ahead and circle this right here and make sure you guys are all aware that this is only for first order reactions, only for first order reactions. So FYI, if on the AP test tomorrow, they start talking about first order, half-life problems, you automatically know it's a first order reaction. Any chemical reaction that has a constant half-life is going to be first order. So just make sure you're looking out for that when you come across a problem. Now, what's super awesome about this kinetics stuff that I've shown you over here, and now that you know it's 0th, 1st, and 2nd order, is that for all three of these, what you're essentially doing is looking for a straight line. The three possible situations are going to be where you graph concentration versus time, the natural log of the concentration versus time, or the reciprocal of the concentration versus time. And in all three situations, if the first one provides you a straight, If the first one provides you a straight line downwards, then you know the reaction is 0th order. If the second one provides you a straight line downwards, then you know it's 1st order. And you know, there we go. And then you know that if the second one provides you an upward facing line, then the reaction is 2nd order. So I want to show you guys how awesome this is. This is one of those things that in the world of chemistry, when you get a question like this on the AP test, you go, heck freaking yeah. I don't even need to read the question. Just stop reading. Don't read. What's the question going to be? Look at the data. Look what it's giving you. You automatically know that the question is going to say, what is the order of the reaction? This one kind of asks it in a slightly different way. It says, explain how the graph indicates the reaction is 2nd order. And they kind of juke you a little bit with this one, which is one of the reasons I don't love this question, because they put the 2nd order graph in the middle and they don't do 0th, 1st, and 2nd. I think that's really kind of cheap, but whatever, that's fine. Because you know that whenever you plot the reciprocal of the concentration versus time and it's a straight line, you know it's 2nd order. And that's pretty much what it says here. The linear graph of 1 over NO2 versus time indicates the reaction is 2nd order. So I love it. When you get graphs like these, you know, the question is going to be, what's the order of the reaction? Now, if they did say or show you that the natural log of NO2 versus time was a straight line, then more than likely one of the subsequent questions would probably be related to a half-life type question. Now, I want all of you to consider this next question here. What is the rate law, not the integrated rate law? What is the rate law of this particular reaction written up above? I'll give you a couple seconds to think about it. All right, cool. Hopefully, you are realizing that if you know that the integrated rate law data tells you that it's 2nd order, then the rate law will be rate is equal to some rate constant times the concentration of NO2 squared. This is the rate law. And then the integrated rate law, if they ask you once again how the concentration of time changes, if the concentration of NO2 changes with time, then you need to use the integrated rate law, which they provide for you. I write it in a slightly different way, but that's okay. The concentration of NO2 is equal to KT plus the reciprocal of the initial concentration of NO2. And boom, if you have these two graphs, you can pretty much answer any algebraic type question. And the last thing that I wanted to go over as far as kinetics goes, because that's pretty much it. It's just these two equations, the collision model. And once again, the last thing that I wanted to discuss was mechanisms. What's super rad about mechanisms is that pretty much the only question you will ever get regarding them is the rate law that we have justifying or consistent with the rate law you come up with? Now, the rate law we had come up with was rate is equal to K times the concentration of NO2 squared. So the rate law must be consistent with this. That's what we came up with in one of the earlier questions. So remember that the slow step of the reaction is always going to be what is called the rate determining step. Mechanisms basically describe rate determining step. Mechanisms basically describe how the chemical reaction will occur. So what they're saying is that step 1, an NO2 is going to collide with an NO2, transferring one of the oxygen atoms to one of the other elements. This NO3 then will spontaneously decompose into NO and O2. And this step here is the fast step. The rate determining step is going to be the step in the reaction in which you can determine the rate law. And as far as mechanisms go, each step, the coefficients each refer to one of the orders of the reaction. Now, for just a regular run-of-the-mill chemical reaction, the coefficients never equal the order of the reaction. This is only true for the elementary steps of the mechanism. So because of this, we know that this particular reaction is going to have a rate law equal to the first step, because that was the slow step. And that's going to be rate is equal to K times the concentration of NO2 times the concentration of NO2. But what's NO2 times NO2? Oh, hey, look at that. That's K times NO2 squared. So since the rate law for the slow step is equal to the overall rate law of the reaction, this is a perfectly fine a mechanism that is consistent with the rate law that I wrote. I'm going to go ahead and clear this in 3, 2, and 1. And I want to go ahead and quickly show you that, yes, step 1 is slow, therefore it's the rate determining step of this mechanism. Notice that rate determining step is always the slow step. The rate law of this elementary step here is equal to those two things combined, and that is consistent with the second order rate law. So once again, always look for the slow step. And then one last kind of fun thing that I wanted to do with this, I wanted to see if you guys could quickly write a reaction coordinate diagram. Let's go ahead and say that this reaction here is overall exothermic. Well, if it's overall exothermic, we know that the reactants will be higher than the products. And my reaction coordinate diagram must show that the first step is slow, but the second step is fast. So the way I can maybe recognize this is by doing a big peak for the second one, and then like a little peak here for the second step, and there we go. Notice first step here, notice the first step has a big activation energy, whereas the second step has a tiny little activation energy. So this first step here is going to be very slow because it has to overcome that barrier. And then the second step here, boom, is quick and easy to move through it. Awesome, awesome, awesome. All right, and that's, once again, pretty much all I wanted to discuss regarding kinetics. Kinetics is one of those units that, you know, is super important. You obviously get a lot of questions related to it, but at the same time, the questions are always collision model, rate laws, or integrated rate laws. So be happy in the fact that you guys will totally crush it regarding those rate laws there. Whew. You guys ready for some thermochemistry? You ready for some thermodynamics? This is also a really fast part. Now, okay, I'm gonna tell you guys this super fun fact. This is one of my favorite things to kind of go over here. And as far as this fact goes, you can share it with your friends. You can do this, but don't share it with anyone that's taking AP Chemistry next year. I can't let anybody figure out this fact because it's always my fun, cool fact. All right. And you guys, oh my God, my actual students. Hi, actual students, if you're still watching this. You guys rock. I can't wait to see you tomorrow. Don't spill the beans, but I don't know. You can't really because it's not there. Okay. Of the 50 United States, 2 of them, so all 50 of them, have never recorded temperatures above 100 degrees Fahrenheit. One of them's Alaska, and that hopefully makes sense. Alaska is super far north. It never really gets that hot there. I mean, it can, but never gets consistently. And yeah, the highest recording temperature, I think, for Alaska is 100 degrees Fahrenheit. What is the other one? Well, the other one is Hawaii. Hawaii has never recorded temperatures above 100 degrees Fahrenheit. And I want to show you here the highest temp for Hawaii. And yeah, the highest recorded temperature for Hawaii is 100 degrees Fahrenheit, which to some people, this is like totally mind-blowing. And it kind of is a weird fact because Hawaii is further south, right? This is not human geography, right? By the way, this is not like a maps class, but it is a chemistry-related fact. Hawaii's highest recorded temperature is 100 degrees Fahrenheit because it's an island. Interestingly enough, me here in Santa Cruz, the temperature doesn't get very hot or very cold, and that's because I'm right next to a large body of water. And so, yeah, this is kind of a fun fact to share, and it has everything to do with the with the what's the word I'm looking for? Specific heat of water. Water has a really high specific heat, and what this means is that it's really difficult to heat this up. Okay, so yeah, kind of a fun fact. Unfortunately, probably the Hawaii fact is not going to come up on the AP test tomorrow. Sorry about that. So let's jump into thermodynamics and kind of talk about the cool things that you will be expected to know on the AP test tomorrow. So up first, really, just what the heck is enthalpy? And I promise you, I'll make sure you're feeling comfortable with this. And in order to understand enthalpy, we need to go through thermochemical reactions and just a little bit more stoichiometry. Last but not least, we'll be discussing calorimetry, the enthalpy of formation, and bond energy. Some quick little problem types that you will be seeing as we move through this. So what is enthalpy? What is enthalpy? Well, enthalpy is going to be a conversion factor. I know that sounds super weird, but enthalpy basically allows for us to convert between heat and the amount of moles in a chemical reaction. And depending on who your teacher is, for me and my students, I generally don't go into more detail about enthalpy because for the AP Chemistry test, it's not necessary. You just need to be able to use enthalpy. So for example, some big takeaways for this is being able to recognize exo versus endothermic reactions. When delta H is negative, the reaction is exothermic. And when delta H is positive, the reaction that we're looking at is endothermic. And what this tells us is that energy is flowing into the surrounding or out of the system, and energy is flowing into the system or out of the surrounding. So we'll just say into system, and this is out of system. And the easy way to see this, right, is exit, right? The word exit, it's out of the system. A lot of chemical reactions are exothermic, but no, there are a lot of very good examples of endothermic reactions. We'll talk about why a lot of reactions are exothermic when we get to the Unit 9 thermodynamics. So for example, I will never get the pen versus pan thing. For example, let's go ahead and check out CH4 plus 2O2, our combustion of methane here. This will produce 2H2O and CO2. It is, first off, incredibly important that without looking at the delta H for this, you should already know if this reaction is exo or endothermic. Is this reaction exo or endothermic? Think about it, think about it, think about it. Well, this being a combustion reaction, it's going to be very exothermic. So it's going to have a negative delta H, and it's roughly negative 890 kilojoules per mole. You don't need to memorize these. They will always provide you the value of delta H for a chemical reaction. Sometimes you'll have to figure out what the value of delta H is for a chemical reaction as well. We'll talk about calorimetry once we get there. But first off, how do you use this value? Well, this value allows for us to convert between the moles of the reaction and the number of the heat that is released or absorbed by the reaction. So the most basic kind of question that you'll see for something like this is 25 grams of CH4 combust. How much heat is released? How much heat is released? Well, when you get something like this, hopefully you're like, heck yeah, I'm so stoked. All I need to go ahead and do is first convert 25 grams to moles. And we do that by using the molar mass. So luckily, the molar mass for CH4 is not too difficult to determine. It's about 16 grams per mole. I know this because there's 1 carbon and 4 hydrogens. And I know that whenever 1 mole of CH4 combusts, because that's the coefficient for CH4, 890 kilojoules of energy is released. So boom, right off the bat there, it's just some basic dimensional analysis. Now, before a bunch of you guys jump on the Q&A part of Fiveable or Discord and go, where's the negative? I want to kind of point out something here. So hopefully if you do this math, you find that it's 1,390 kilojoules of energy. And boom, where's that negative? Well, in the question, it told me that that energy is released. There's no such thing as negative heat. Remember, negative heat is just indicating that the direction of the reaction. So in this situation, because I told you where the heat is being released to, all you need to go ahead and do is maybe add a statement saying, hey, 1390 kilojoules was released. Or in this situation, since it's already asking you to determine how much heat was released, all you need to go ahead and do is write 1390 kilojoules. You don't need to include the negative. And I think conceptually adding the negative would be pretty bad for a situation like this. Enthalpy is a conversion factor. Enthalpy is a conversion factor. So as far as this goes, I do want to point out that we can calculate heat using probably the most famous equation from chemistry other than PV equals nRT, using Q equals MC delta T. Q here is the quantity we use for heat. M is going to be mass. C here is the specific heat, and specific heat is the quantity that tells you how much energy is required to raise the temperature of 1 gram of substance. And delta T is the change in temperature, So what's really cool about this is I do want to point out that you can use Q equals MC delta T in accordance with like an enthalpy problem, because we just determined Q up here. But we'll come back to that. Let's just make sure that we're comfortable using the equation Q equals MC delta T. Oftentimes what they'll do is they'll provide you with some sort of question along the lines, actually, let's do that. If you jump over to the finale slides, I think the next question, boom, is down below. It says, calculate the magnitude of the heat energy in kilojoules absorbed by the water. Assume that the energy released from the combustion is completely transferred to the water. And they give you all of this data. I'm going to give you guys about 2 minutes to try this one out here. But I will give you a hint. For this particular problem, it's going to be Q equals MC delta T. About 1 more minute. About 1 more minute. There's a good Discord question that I want to go over really quick once we finish with this. It's the delta H question. So yeah, I'll go over that really quick. All right, so hopefully we found in this particular situation that for this, you only need to use the specific heat of water. And when this chemical reaction occurs of the combustion of C3H7OH, it's allowing water to escape into, allowing heat to escape into the water and heat up the water. So if you use Q equals MC delta T, the mass of the water that you are heating is 125 grams, and the difference in temperature is going to be 51.1 minus 22 to find about 15.2 kilojoules of energy is required to heat the water up by that much. Now, one of my favorite FRQ experimental error type questions would be something along the lines of this. We expected when, like, for example, we transferred 15.2 kilojoules of energy to this, for the temperature of water, the final temperature of water, to be 51.1 degrees Celsius when it started at 22. How come the reaction did not end at 51.1, but rather something like 49.1 degrees Celsius? How come it's lower? Well, the easiest answer for almost any experimental error type question that you will see related to thermochemistry is that heat oftentimes escapes into the surrounding and not where you want it to go. Surrounding is a great answer for this. It's not always going to be the answer, trust me, but a lot of the times it will be. Once again, when we're talking about heat escaping into the surrounding, it's almost always going to be, how come this thing didn't heat up as much as it should have? So just keep that on the back of your mind. Now, one thing that we can do, and I was kind of referring to this as well, and after this FRQ, I'm going to still continue talking about thermochemistry in more detail, but you can relate these values that we found and the chemical reaction up above to answering something along the lines of this. So once again, I'll write it out for you guys. We needed 15.2 kilojoules. That was our answer from the last one. Based on the experimental data, if 1 mole of C3H7OH is combusted, how much heat in kilojoules is released? Report your answer with the correct number of significant figures. So we found 15.2 in the last section. Actually, we need one more piece of information. We need, the amount of C3H7OH that combusted, which was 0.55 grams. So make sure you include that as well. Boom, boom, boom. And I'll give you a couple seconds to kind of consider what you need to do in order to answer this. But basically, it's asking how much heat in kilojoules is released when 1 mole is combusted. Well, interestingly enough, so I'm back. I know I'm not using my subtle voice when I come back. Sorry if I'm making anybody jump. What you need to do is actually use this as a conversion factor. When 15.2 kilojoules of energy is combusted, is produced, 0.55 grams of C3H7OH combusted. So essentially what this looks like is that we know that 1 mole of C3H7OH will be converted into grams using the molar mass of C3H7OH. And fortunately, in this particular problem, it did not give you the molar mass. But in other problems, they will sometimes give you the molar mass, which is super nice because if they give you the molar mass, then you don't have to calculate it. But yeah, okay, in this one you do. And then there's that conversion factor that I went ahead and told you guys. Now, you did get 1 point for correctly getting the kilojoules, but you did not get the correct point if you didn't convert to the correct number of sig figs. We calculated in the data table. I'll go ahead and show you guys again that it's 0.55 grams. And because of that, your final answer should have 2 significant figures. Now, as far as the 1 mole goes, these are exact values, so they have an infinite number of significant figures, so don't fall into that trap. Now, the last thing that I want to discuss about thermochemistry is different ways that we can go about determining the value of enthalpy. And some of the easy ways to do this is through heat or enthalpy of fusion. Now, before I jump into that, like I said, there was a good question that came up in Discord that I want to talk about really quick. And the Discord question was, I'll go ahead and stop sharing here. Is delta H and H the same thing? And the answer is not really. H is defined in a very important specific way, but delta H is what you will only ever see. Delta H is the change in enthalpy for a chemical reaction or process, and we're basically only ever looking at the initial and final state, or the final and initial state. The reason that you will never see the value of H is based on how it's defined, which is a function of the internal energy of the system. And unfortunately, it's impossible to determine what the internal energy is based on how particles and molecules are. That sounds super funky, but it's really easy for us to measure the difference in enthalpy values. So you'll only ever see delta H. I've been abbreviating it as just H. That's my bad. So let's go ahead and look at heats of formation or enthalpy of formation. And once again, this is really just a way for us to identify the value of the change in enthalpy for a reaction. So once again, the enthalpy of, sorry, I thought I hit it. There we go. The enthalpy of formation is a thermodynamic quantity that will always be given to you. It's delta H, and they represent it with a little f. If they do this, you know exactly what equation to use. But just for quick definition's sake, the enthalpy of formation is the amount of energy required to make 1 mole of a substance. And this will always be used in the following way. Delta H of reaction is equal to the sum of the heats of formation for the products minus the sum of the heat of formation for the reactants. And luckily, if you look on your reference sheet, they provide this to you right, I think I need to go this way, here. Delta H is equal to the heat of formation of the products minus the heat of formation for the reactants. Now, the reason that I'm bringing this up to you guys is because, unfortunately, if they give you bond energy, you cannot use the same equation. Bond energy is defined as the amount of energy required to separate amount of energy required to break a bond, or 1 mole, if you will. And so for this, if they ever give you bond energy data, there's oftentimes going to be a Lewis structure type question associated with that. And so if they ever do that, notice it's always going to be in this form where the delta H of reaction is equal to the bonds broken minus the bonds formed. And what's really happening here is that we break the bonds in the reactants and we form the bonds in the products. And this kind of seems like it's backwards from the other formula. So, and it is. So you just need to make sure that you look at and see that the delta H of delta HF is different than the reactants and products one, okay? So just make sure you're looking at bond energy versus heat of formation. So make sure you're on the lookout for that. All right. We're going to do thermochemistry in more detail at the end when we go over thermodynamics, but really that's the big takeaways from that unit. Both Unit 5 and Unit 6 are super short and relatively straightforward. The problem types are almost always the same, and you will crush any questions that you see related to those. All right, we are on to the last 3 units, and we got plenty of time to do this. We're going to be talking about equilibrium, acids and bases, and thermodynamics, okay? Equilibrium is a pretty consistent problem type once again, so we just want to make sure that we're comfortable with the whole products over reactants process, and we also want to understand ice tables. Once we get into acids and bases, which I know is what a lot of you want to discuss and talk about, we'll talk about acid-base reactions, along with titrations and titration curves. And then we'll end by talking about thermodynamics, some of the important things that you should see with that. So let's go ahead and jump into it. Let's go ahead and get into a little bit more detail here, talking about equilibrium. As far as equilibrium goes, don't forget the equilibrium condition. Really what this is that it's saying that a chemical reaction is at equilibrium when the rate of the forward reaction is equal to the rate of the reverse reaction. Oftentimes, they will try to trip you up by saying that equilibrium is when the concentration of the reactants and products are equal, and that is not true. That is absolutely not true. That is not true. Equilibrium is when the forward rate of reaction is equal to the reverse rate of reaction. The equilibrium constant and expression is the expression products over reactants, and the reaction quotient is one of the main ideas and concepts from this, which helps us identify the direction of the reaction. Last but not least, we'll spend some time talking about the solubility product by looking at how to determine the concentration of ions in solution. So let's go ahead and jump into looking at the equilibrium expression. And the equilibrium expression is pretty much always going to be for any chemical reaction, capital K is equal to the concentration of the products raised to their coefficients divided by the concentration of the reactants raised to their coefficients. As far as products over reactants goes, as far as this expression goes, whenever you see a K, whether it's KC, KP, KSP, KW, KA, or KB, this expression will hold. And for whatever reason, when we get into like KSPs or KAs and KBs, students seem to forget this, but guess what? The chemical reaction is always the same. Now, as far as these last 4 K values go, they probably do expect you to know what the chemical reaction is, but KSP is just referring to an ionic compound dissolving into water, Ka is referring to an acid giving water hydrogen ion, and Kb is referring to water giving a base a hydrogen ion. Let's go ahead and look at a problem type for this and remind ourselves what the ice table is. So I'm going to totally make up these numbers. This has no bearing as to what the actual values for K for this chemical reaction are, so don't quote me on that. But the way we solve this problem type is pretty much consistent throughout. Let's say we have hydrogen gas reacting with chlorine gas, and it's at equilibrium. It's at equilibrium with 2 hydrogen chloride molecules, HCl. H2 plus Cl2 makes 2HCl. And we're looking at an ice table type problem. You see ICE. And the question tells us the initial concentration, or we'll say initial pressure, of H2 is, we'll say 1.5 atm. Chlorine gas is 1.5 atm. And hydrogen chloride is also 1.5 atm. And the K value is provided for this reaction. Once again, do not quote me on this. We'll say that the K value for this is no, let's definitely not use 1.5. Let's do like 7.2 times 10 to the -3rd. Now, K, equilibrium constant here, is always going to be a unitless value. So I'm gonna come back to the ice table here in a second. But K will always be unitless. Sorry. Unitless and temperature dependent. So one of the ways they will try to mess you up a little bit is by saying at 35 degrees Celsius, at 412 Kelvin, K is this. And that's fine. They just need to tell you the K so that you know that it is for that particular value. So it's temperature dependent. And K, being a couple values, tells us certain things. When K is greater than 1, it's telling us that the products are favored. And when K is less than 1, it's telling us that the reactants are favored. And hopefully this kind of makes sense mathematically. Because when K is bigger than 1, go back to our equilibrium expression, that's telling us that the number on top here is greater than the number down below, products over reactants. And if K is less than 1, that means the reactant value is greater. And at equilibrium, the concentration of the reactants is greater. So now that we kind of have a little bit of a baseline understanding here, let's go ahead and check this out. Well, K is significantly less than 1, right? K is 7.2 times 10 to the -3. This tells us that the particular reaction that we are looking at, is heavily reactant favored. Now, we do still need to calculate Q. Ooh, sorry, that was weird. Q, there we go. And Q can be found by determining, using the equilibrium expression, but using the initial concentration. So this would be HCl squared divided by H2 divided by Cl2. And hopefully you guys can see that for this particular problem, I'll actually kind of come back here. Q is going to be 1. Q is equal to 1 because this is 1.5 squared divided by 1.5 squared. So since Q is greater than K, because K was 7.2 times 10 to the -3, and Q was 1, this is telling us that the reaction shifts left. The reaction will shift to the left. The reaction shifts to the left. Now, as far as our ice table goes, that tells us that this will increase in concentration. This will increase in, not concentration, partial pressure, and this will decrease in partial pressure. The only values that we can put into our equilibrium expression is partial pressure or concentration. Now, the change will always be stoichiometric. So it's going to be plus 1x, and minus 2x. And the equilibrium value here is always going to be these two columns summed up. So 1.5 plus x, 1.5 plus x, and 1.5 minus 2x. And what this allows for us to do is then do some interesting math. So let's go ahead and say that I wanted to determine the concentration of the partial pressure of Cl2 at equilibrium. then what I could go ahead and do for a particular problem like that is then establish or set up the equilibrium expression, which was, K is equal to the concentration of HCl squared divided by H2 times Cl2. And we know that 1.5 minus 2x squared over 1.5 plus x squared, right? Notice that H2 and Cl2 were the same values here. And I'm just going to go ahead and pull up the value for K one more time, which is right here. And we can go ahead and quickly solve for the K value in that way. So that's equal to, oh gosh, sorry about that. 7.2 times 10 to the negative 3. 7.2 times 10 to the negative 3. And solving for x should always be a somewhat easy thing. In this situation, we can see if we square root both sides, we can go ahead and determine, I don't know why I did that, that was kind of weird. We can go ahead and solve for x pretty easily like that, okay? Now, this not being a math class, I don't want to go into the specifics of this because there are other chemistry type questions that I can solve for. But really quickly, I'll set you up with the last little thing, and then you can solve for x if you want to on your own. Plus x there is equal to, and then 7.2 times 10 raised to the negative third. This would be 8.49 times 10 to the negative 2. And yeah, this math gets a little ugly, it gets a little gross, but it's not terrible. It's not too bad. I wanted to show you one more FRQ type question from the equilibrium section, and that's related to this. So notice that a lot of times for the FRQ questions, they will go ahead and ask you to write out the equilibrium expression. For this one, it just wants you to quickly do this. I will point out, I will make sure you guys see this and understand this, that for the equilibrium expression problems, if they do not ask you to write it out, you should still do it because oftentimes they will give you extra points for it. For this, it's products over reactants. So we see that it's Kp is equal to the partial pressure of NO squared divided by the partial pressure of nitrogen gas times the partial pressure of oxygen gas. So as far as this goes, Kp equals this divided by these values here. That's pretty much what you need in order to get the points for this question. So voila, there you go. I do want to point out that oftentimes we talk about the concentration and we use brackets for those values. Don't get too tripped up with those. Don't get too tripped up with those. It is definitely necessary that you include pressure for these problems here. Now, using that Kp, I'll go ahead and rewrite it for you guys up here. So Kp is equal to the partial pressure of NO squared over the partial pressure of N2 times the partial pressure of O2. I want you guys to go ahead and answer this question, but I want you to go ahead and answer this question after you go touch your front door. This is your last little time to move around. We got 1 hour left, and it is so important that you have good blood flow and good motion and good everything for this. So I'm gonna quickly stop sharing. Okay, everyone's here with me. Don't be with me for about 2 seconds. Go touch your front door. Go wiggle it out. Last little thing. Rufus is asleep up front. Otherwise, I would totally bring him back again. But I think if I woke him up one more time, he might be a little upset. And when you get back, we'll go ahead and do this last problem here. So shake it out, and then we'll be back. 1 hour, 1 hour left. You come in. He actually wanted to say hi, but I actually think I know why he's back here. Come on. Can you come up here? Can you come up? Oh, he's 2 bananas. He wants dinner. I want dinner too. Hopefully, please tell me you guys have eaten. Make sure you eat some good food. Don't forget that when you guys are eating food, make sure that when you're eating food, you are checking out and trying like high calorie, high carbs. These will keep you kind of full and ready to go tomorrow. And also, when I'm talking about high calorie, I want to make sure you guys are like, I want to make sure that you guys are, what's the word I'm looking for? Not eating like sugar and like Red Bull and stuff like this. You want to have like good sugars, right? Like fruits and vegetables. Bread is okay. Some good carbs is okay. Stuff like that, okay? So make sure you guys are checking that stuff out. What's the Google extension? It's just like some free thing I found online. It's like Super King in Discord. It's like what's it called? Let me see if I can find it. Page Marker. It was free. It works. Jolly Ranchers. Sorry. I'm so sorry. I'm so sorry. I'm not calling you guys out. I'm just saying like good food. Oh goodness. Sorry, that's my Discord. Nice. All right, cool. All right. Here, one more Rufus. Hi. Come on. Here, say hi. He goes, hi. I'm Rufus. I do chemistry. All right. Come on. 2 points. I have to kick him out of the back room because the back room is where the back room is where I keep his dinner. So, yeah. All right. Hopefully you got your wiggles out. This is our last hour. This is our last hour to get some good, meaningful chemistry in for this. We're going to finish up really quickly here, our equilibrium unit. And then I want to spend some time on acids and bases. I think a lot of you guys do as well. Acids and bases is a little bit bigger part of the AP test. So we'll spend a good few minutes on this, and then it's the end. Hopefully, if I have time, I can do my graph game at the end. It's a good little way to end our unit here, our stuff off. Okay. Oh my good lord. There is a dog doppelganger in Discord. Lily Grace, what the heck is happening? All right, cool. So here we are. There we go. As far as a problem like this goes, being able to recognize and walk through an ice table problem pretty quickly is super important. So I just want to quickly set this up one more time and kind of show you what you need in order to do something like this. So what I always like to do for my ice tables is rewrite the chemical equation. So N2 plus O2 is at equilibrium with 2NO. And then I like to go ahead and write all of the important values out for it. So as far as this goes, it says that N2 has an initial partial pressure of 6.01. O2 has an initial partial pressure of 1.61. And then there is no NO given to us. So as far as this goes, we know we have to shift to the right. Always move in the direction of the zero. So this is going to be minus x, and then plus 2x. As far as this goes, we know that this value here at equilibrium is going to be 6.01 minus x. This is going to be 1.61 minus x. And they tell us that at equilibrium, the partial pressure of NO is 0.122. So quickly, we can go ahead and determine, since I plus C equals E, I plus C equals E, 2x is equal to 0.122. X is going to equal 0.061. And if we plug all of the known values after we solve for the x here, and back into the Kp, we can go ahead and find, voila, that the Kp for this particular reaction is 0.00161. So don't forget that K is a sorry about that. K is a unitless temperature-dependent value. And as far as this goes, this also tells us that the reaction is heavily reactant-favored. Sorry. And it's reactant-favored because K is less than 1. I said heavily reactant-favored, but maybe not so much there. All right, guys. You want to do some acids and bases? I feel like we need some more pump up music, but I already used that today. So it's just like acids, bases, go, go, go. I was a cheerleader in my past life, maybe. Well, I was in marching band. Is a marching band? That's kind of a cheerleader. A little bit, right? All right. So as far as this goes, acids and bases, you guys totally got this. I'm going to show you the main couple things that you need to take away from this. It's always super frustrating or scary when you go into acids and bases because there's a lot of stuff that seems to be happening with this. But I do want to point out that there's really only a couple things that you need to know for acids and bases. And that's the following. You need to be comfortable with the pH and pOH equations. I'm going to go ahead and write those up in a second and just make sure you know when to use them. You also need to know the strong acids and bases and the weak acids and bases. But as far as weak acids and bases go, there's a huge giveaway for when we're talking about weak acids or weak bases. And then the dreaded titrations. I'll make sure that we look at, before the end of today, a couple of interesting titration type things that could come up. And then we are on to our last unit. So as far as acids and bases go, we want to make sure that we're comfortable with our pH equations. The big pH equations are given to you on the, not periodic table, the reference sheet here. Sorry about that. Oops, I don't know why that did that there. And they can be found right here in the equilibrium section because acids and bases are really just some equilibrium type chemistry. Now, I do want to point out that they give you the Ka and Kb equations, but what this is really telling you is that we're kind of showing you what the reactions are. The reactions for Ka can be basically shown to be HA turning into H plus and A minus. And Kb, right, if it's products over reactants, is going to be some sort of base reacting with liquid water, so L here, to go ahead and form this conjugate acid along with the hydroxide ion. I didn't write the state of matter for any of these things here because they were aqueous. Remember, liquid substances do not get included with the equilibrium expression. So these values of K, though, are still products over reactants, and that's the kind of point I wanted to make with that really quickly. And we'll go into more detail with that. The pH equations right here, pH is equal to the negative log of the hydrogen ion concentration. The pOH is equal to the negative log of the hydroxide ion concentration. And 14 is equal to the pH plus the pOH. pK and pKb are also listed down below. This equation is the Henderson-Hasselbalch, and that's how you determine the pH of a buffered solution. So with that being said, now that we know where all those equations are at, we can kind of understand and go into a little bit more detail about what a strong acid versus a weak acid is, and what a strong base versus a weak base is. So a strong acid completely ionizes. And what I mean by this is that when you place a strong acid into water, and there are 6 strong acids and you need to memorize them, they will completely dissociate or ionize into solution. It's HCl, HBr, HI, HNO3, HClO4, and H2SO4. You need to memorize these because all 6 of these will completely ionize when they're placed into water. The ionization looks like this, where if we take something like nitric acid, it will react with water, donating a proton to that water to go ahead and produce the nitrate ion along with, scoot you up just a little bit there, the hydronium ion. Now, in the world of chemistry, hydronium is essentially the same thing as the hydrogen ion. They're not identical, but they work well enough. When we are talking about strong acids, notice that there is no equilibrium. For this, there is no equilibrium. So as far as that goes, there is basically only a stoichiometric calculation for this. If you have 10 moles of HNO3, it's going to produce 10 moles of H3O+. If you have 27, 27. If you have 2, you have 2. Basically, in the world of acid-base chemistry, the main thing you are looking for is H3O. Whenever you can find this, notice that you can jump back into the equations and pretty much solve for anything that you were looking for. If you know the concentration of H3O, you can find the pH. If you know the concentration of H3O, you can find pH and then the POH. If you know the concentration of H3O, you can find pH, then POH, and then the concentration of OH. I also want to point out that we also have this equation here, which relates the concentration of H plus and OH minus, which comes from the auto-ionization of water. And yeah, I'm not going to worry too much about that here. As far as that goes, when I go ahead and look at strong acid completely ionizing in solution, the concentration of the strong acid will equal the concentration of the hydronium ion. So pretty much you just need to take the negative log of that in order to find the pH of the solution. Let's go ahead and look at weak acids, though. Weak acids are a little bit funkier. And even with an hour left, I'm not going to be able to figure out that I need to click a certain thing. All right, if strong acids completely ionize, what do you think weak acids do? They don't completely ionize. They do not completely ionize. And so what that means is we establish equilibrium. Let's go ahead and look at, for example, acetic acid, HC2H3O2. When I place this into water, it will still donate a proton to water. It's going to give this proton to water here. But what ends up happening is that most of this will not react. Most of it stays as HC2H3O2. We produce a couple of hydrogen ions or hydronium ions in solution and a couple of acetates in solution, but not very much. How do we quantify a chemical reaction that's at equilibrium? Well, we do that with a value of K. And for this, H3O plus is aqueous. Sorry. And this is aqueous as well with the minus sign. We quantify this with the Ka value. So the Ka basically talks about any acid reacting with water. So it donates the proton to water to make H3O and whatever the conjugate base is. The Ka for acetic acid is 1.8 times 10 to the negative fifth. And since this value is so much less than 1, you can easily see that this value is heavily reactant favored. So as far as this goes, as far as this Ka goes, we use this in order to determine the pH of the solution. So let me go ahead and show you how I can determine the pH of a solution for anything as long as I just know the Ka. Let's go ahead and say that the Ka for a reaction is let's do like 1.22 times 10 to the negative 6. This is a pretty small Ka value, which means that my acid is fairly weak. Well, one way that I can determine the pH for this solution, and if you are ever asked to determine the pH for a weak acid, all you need to go ahead and do is set up the ICE table. And whatever that acid is, some sort of acid reacting with water, it's going to donate that proton to water here, and we have this equilibrium established, producing the hydronium ion and the conjugate base. The last thing that I need, and I forgot to provide you with, is going to go ahead and be the initial concentration of HA. So they'll say, like, what is the concentration of this acid? What is the pH, excuse me, of this acid, given that its concentration is like 0.1 molar? Doesn't matter what it is, whatever the initial concentration, we can go ahead and just place into here. Now, as far as these ice tables go for the acid-base reactions, the water will always be crossed out because the water is always liquid. And so remember, for ice tables and equilibrium type problems, we don't need to include the water. The initial concentration of H3O and A- are automatically 0, and so we don't need to include those with these problem types. Now, here's where it gets kind of fun. Because the value of K is so small, the change for this is going to be negligible. You can almost always disregard the x. So 0.1 minus x essentially is going to equal 0.1. We know that plus x and plus x values are going to be here. And as far as that goes, that's the rest of this ice table. Notice that I haven't identified what this acid is at all, and that's okay because every single one of the calculate the pH of this weak acid will be the same. When I go ahead and then throw into my equilibrium expression, which is going to be, Ka is equal to products over reactants. So notice it's going to be H3 plus times A minus divided by the concentration of HA. And what this essentially becomes is x squared over the initial concentration, right? Products over reactants. And this was equal to 1.22 times 10 to the negative 6. 1.22 times 10 to the negative 6. Now, what's super frustrating about these problem types is that what I could go ahead and do pretty easily here is solve for x. And like if this was a math class, what I would want to do is, what I would want to do is pretty much finish when I solved for x. So when I solve for x here, I find it's 3.49 times 10 to the negative 4th. Now, like I said, what's frustrating about this is that I asked for the pH, and I haven't finished this yet. Whenever I get an x value after setting up an ice table, please do me a favor and reread the question. If you don't reread the question, then you might kind of mess up and see that, oh, you actually haven't answered the rest of the question. So we know that at equilibrium, the concentration of H3O plus, we know that the concentration of H3O plus is 3.49 times 10 to the negative 4th. And all I have to do to go ahead and finish this problem is quite literally take the negative log of this value. So sorry, I am always forgetting to click the pen. I think it's because Zoom has a different functionality for that. So I'm like trained already to do that button. So pH is equal to the negative log of 3.49 times 10 to the negative 4th. Negative log answer, which is going to be 3.46. The pH is 3.46. pH is a unitless value, by the way. pH is a unitless value, by the way, so you don't need to worry about adding any sort of units after the fact for this. Now, that is the main problem type for determining the pH of a weak acid. You basically just set up the ice table and go from it there. Now, up next, we want to make sure that we're comfortable with acid-base reactions. I talked briefly about acid-base reactions in Unit 4, but I really just said their names. I said acids and bases will react. So let's go ahead and define what an acid-base reaction is. An acid-base reaction is going to be when protons are transferred. So if they ask you, how do you know it's an acid-base reaction? I don't know what happened there. Boom. This is going to be when a hydrogen ion is transferred. These protons here, these protons basically define how the chemical reaction is going to occur. You know it's going to be in the acid-base style. So acid-base reactions when H plus is transferred. As far as this goes, you will pretty much always produce a salt and water. So for example, when we're looking at an acid-base reaction, we could do something like HCl reacting with NaOH, a strong base, and this will end up producing sodium chloride and liquid water. What ended up happening is the hydrogen ion was transferred and provided to the OH, and then the NaCl just ended up combining in that fashion. This is a great example of an acid-base reaction. Now, what's really cool about these particular types of questions is that you can, excuse me, what's really cool about these types of reactions is that you can actually do some cool stoichiometry with them. Usually we need some sort of indicator. An indicator is a species, is a substance that changes color based on the pH. So let's go ahead and check out a really basic type of titration question. The way that these questions will end up working is they'll tell you the concentration and volume of a certain substance and then ask you for the concentration of another species. So let's go ahead and try something along the lines of this. I actually think there's a good, let me see if I can pull this up here. I need to remind myself where it's at. There's a good multiple choice question here that I'm going to go ahead and share with you guys. This multiple choice question can be found with a couple other multiple choice questions in the College Board course and exam description. So if you go online and literally just do AP Chemistry course exam and description, you'll find this document here. It's publicly available to anybody that wants to check it out. Sorry, I need to make this a little bit smaller so you guys can see it. And boom, boom, and how come you're not opening up? Oh, there it is. So hopefully you guys can see, yeah, this great multiple choice question up above. I want you to try this out, and here's my advice. Try it out without a calculator. So this is a great multiple choice titration type question that you must be able to answer without a calculator. I'm gonna give you guys about 3 minutes to try it out. All right, guys, you have about 90 seconds left, to try this problem out. Once again, try to answer it without a calculator. Or about 30 seconds left. I want to give you guys a quick little hint with a problem like this. When we're looking at, ooh, shoot, I can't write on this one here. Let me do something really quick here that will allow for me to write on this. All right, sorry, y'all. Give me a second here to get where I need to get. Boom, boom, boom. Thank God this document is findable on the interwebs. All right. Just need to get the right question here. There it is. All right. So I'm just going to quickly change gears. I had this on a PDF, and I realized that I can't write on PDFs. Sorry about that. Boom, boom, boom. Cool. Okay, yeah, I'm on the right spot. All right, so for a problem like this, y'all, all you need to do is first write the balanced chemical equation. So it's going to be magnesium hydroxide, MgOH2, reacting with nitric acid, HNO3. Like I said, you're always going to produce water for these reactions and a little bit of a magnesium nitrate, so MgNO3, 2. Nitrate has a -1 charge and magnesium has a +2 charge. So it's a 1-to-2 ratio. And then voila, 2-to-2 ratio. We can see here that the burette is reading 2.17 to 22.17. So the volume added was 20.00 milliliters. And then with the rest of the problem, it tells us what we need to know. An antacid tablet contains magnesium hydroxide. It's titrated with a 0.1 molar solution of HNO3. The endpoint is determined by using an indicator. So voila, we know that we added 20 milliliters of HNO3. And we know that the molarity equation is moles per liter. So molarity, if it was 0.1, and we're solving for moles here, then 0.1, right, times 0.02, x will equal 0.002. Once again, this mental math is something that you are expected to know, and this is moles of HNO3. Now that we know, I know I'm kind of writing all over the place, but now that we know it's 0.002 moles of HNO3, we just then do some dimensional analysis here where it's 2 mole of HNO3 for every 1 mole of MgOH2. And we know at last that for every 1 mole of MgOH2, it's 58.3 grams. So 2 will cancel this and turn it into a 1, and then it's 0.001 times 58.3. So we just need to scooch this decimal place once, twice, 3 places over. Our final answer is going to be A. So I do want to point out that there are a couple multiple choice questions that you can go ahead and check out in the course exam and description. It's quite easy to Google. I'll show you what I did. I'm going to go ahead and clear this here in 3, 2, and 1. And look what I did. I literally just Googled AP Chem course exam and description. Now, the last thing that you should be comfortable regarding acids and bases is going to be those titration curves. There are 3 situations that you can look at, 4, but 2 of them are pretty much the same. So you can always titrate, an acid or a base with something that is strong. So the titrant will always be strong. So there's strong acids and strong bases. As far as the acid and base titration goes, there are going to be 4 scenarios here. Once again, 2 of them are pretty much the same. If we are titrating a strong acid with a strong base, let's go ahead and write it like this. We're going to titrate a strong acid with a strong base. then the way that the titration curve will look, it's always going to plot pH. It's always going to plot pH versus the titrant added, the volume of the titrant in milliliters. Then a strong acid with a strong base will start off low, come up, and end flat. The pH at equivalence will be 7. So this point right here is what we call the equivalence point. And vice versa, if I go ahead and titrate a strong base with a strong acid, then you start high, curve down, and flatten out. And same thing here, the pH is going to be 7 at equivalence, the 7 at equivalence. Where it gets a little funky and weird for these is the equivalence point, the pH for the equivalence point of weak acid, strong base titrations. So as far as this goes, a weak acid with a strong base will always look like this. Essentially, first you kind of dip down and then flatten out, and then it comes back down again and then flattens out again. If your pH is, if the pH is 7 here, the equivalence for a weak acid strong base titration will always be above 7. I actually screwed this up. Sorry about that. So it kind of flattens up and then flat like that. So if my pH is 7 here, the equivalence point will always be at a pH above 7. So equivalence greater than 7 every single time. And then as far as the other situation or scenario here, we're going to essentially be looking at a weak base strong acid titration. And what's happening is kind of what I drew that first time. I just drew it for this scenario here. The equivalence point is going to be less than 7. So once again, if 7 is roughly right here, at equivalence, the pH will be less than 7. Equivalence less than 7. Oh, dang it. I screwed that up. There we go. Greater than. Equivalence is greater than 7. Sorry about that, y'all. Greater than 7. These are weird multiple choice questions that always come up for acid-base titrations, and just being comfortable recognizing that you're dealing with a strong acid, weak base, or weak base, strong acid type reaction, knowing where the pH at equivalence is crucial. It's super important, and usually it's a pretty straightforward question. Let me go ahead and show you what I mean by this. If we look at a scenario here like the following, let me go and pull this up here. Wham, bam, there we go. We can see that in a question like this, it says, for each of the following statements, determine whether the statement is true or false. In each case, explain the reasoning that supports your answer. So in this question here, we are at equivalence point. The equivalence point is when you mix the exact same amount of moles of acid as you do base. So in the situation here, because I mixed 50 milliliters of 0.2 molar acid with 50 milliliters of 0.2 molar base, we know we're at the equivalence point. Is this one of the 6 strong acids? Absolutely not. So we know that it does not react or ionize completely, and therefore the pH at this equivalence point should be above 7. And hey, look at that. This is a false statement. The conjugate base of a weak acid undergoes hydrolysis, or once again, goes through some sort of chemical reaction with water, taking a proton away and changing the amount of OH in solution. The next part of this question is also a kind of titration-esque question. It says this: if the pH of a hydrochloric acid solution is the same as the pH of a propanoic acid solution, then the molar concentration of hydrochloric acid must be less than the molar concentration of propanoic acid. And the answer to that is totally true. HCl is a strong acid. Being able to recognize the 6 strong acids is crucial for answering kind of weird qualitative-esque type questions in this context. All right, With that being said, ladies and gentlemen, I want to move on to our last unit, where 20 minutes is more than enough time to cover the cool stuff that we need to talk in regards to thermodynamics. Thermodynamics is the unit relating to how the reactions are thermodynamically favorable. And that sounds like a weird statement, and I always tell my students, like, yeah, you should probably know what thermodynamically favorable is, but at the end of the day, if you just recognize that a reaction is thermodynamically favorable or not, you're pretty much good to go. You just want to recognize whether or not this reaction that I'm looking at has a positive or negative delta G. And so in order to do that, so we're going to go ahead and jump into this here, we need to define a few things. And the things that we need to go ahead and define are entropy. We need to do a little bit of a review of enthalpy, and we need to define Gibbs free energy. And what's really cool is that there is a kind of tie-in at the very end to electrochemistry, where we'll spend a few seconds discussing and talking about that. So first off, what is entropy? Well, entropy is the measure of disorder or randomness. Entropy is the measure of disorder. And in regards to this, and basically whenever we discuss this, we want to be extremely confident and comfortable understanding that a chemical reaction that increases in entropy is getting more chaotic. So for example, if I look at something along the lines of 2SO2 gas plus O2 gas turning into 2SO3, well, in this situation, since all the states of matter stay the same, and because you're going from 3 molecules down to 2, the change in entropy will be negative. Because once again, for this particular situation, it did not get more crazy. It did not get more disordered. In another situation where I have something along the lines of H2O solid turning into H2O liquid, we call this process here melting, and the change in entropy for this situation would be positive because liquids have a greater kind of chaos or disorder associated with them than the solids do. Now, what's really interesting is that both of these chemical reactions totally can happen and totally can be thermodynamically favorable, but one of them is more favorable than the others. And this has to do with the second law of thermodynamics. The second law of thermodynamics basically says this. Of course, you write when I don't want you to write. The second law of thermodynamics basically says that for any process, second law of, we're just going to say therm, any process must increase the entropy of the universe, must increase entropy. But once again, if we looked at those examples up above, I told you guys that both of these reactions occur. So is this first reaction here breaking the second law of thermodynamics? What about the reverse of this, where H2O liquid turns into H2O solid? That would totally have a negative entropy change. Does that break the second law of thermodynamics? And hopefully if you're sitting here thinking like, wait a minute, water definitely freezes. I want you to remember that we are increasing the entropy of the universe, And so these chemical reactions, while they're really cool, they are not the universe, okay? So there's something else that's going into play with this, and that's actually enthalpy. So we're gonna come back and talk about enthalpy really quick. Remember, if delta H is negative, this is exothermic. And what this does is it increases the entropy of the surroundings. Surroundings entropy goes up. And if delta H is positive, it's endothermic. And what's happening here is you remove energy from the surrounding, and the surroundings entropy goes down. Entropy goes down. And so what's happening here is that in order for us to understand whether or not something is thermodynamically favorable or not, we have to include not just entropy, but also enthalpy of the chemical reaction. And what I want to provide you guys is with an excellent chart, which will be super important for determining quickly some of the qualitative identities of whether or not a reaction is thermodynamically favorable or not. So delta H and delta S can either be positive or negative. Well, we know that when delta S is positive, the entropy for the reaction increases. And we know that when delta H is negative, the entropy for the surrounding increases. So basically, in these situations, when we ask thermodynamically favorable, dynamic favorability, this will always be thermodynamically favorable. Once again, when delta H is negative and delta S is positive. And that must mean when the signs are opposite, it's never thermodynamically favorable. Now, technically, this doesn't mean that the reaction will not occur. It's just that in order to get that reaction to occur, you need to input work. You need to do some sort of outside intervention, if you will, okay? Now, there are a couple of other situations, and these situations are pretty straightforward to memorize because of the way the signs work. If delta H and delta S are both negative, the only time these reactions will be thermodynamically favorable is at low temperature. And what do negative numbers mean, right? Low, so that's how I remember this. And when both delta H and delta S are positive, this is going to be at high temperatures, And once again, positive numbers indicate high. Now, this is relatively low and relatively high, so just be on the lookout for these values. Now, some really smart scientists came around. I'll let you kind of figure out what his name is. And he figured out that by relating delta H and delta S, we can come up with another thermodynamic value and always determine the thermodynamic favorability of a reaction. And this is Gibbs free energy. Gibbs free energy will be represented with a delta G, and this will basically tell us whether or not a reaction is thermodynamically favorable or not. If delta G is negative, the reaction is spontaneous or thermodynamically favorable. If delta G is positive, it's not. So once again, thermodynamically, I promise I could spell, I promise, dynamically favorable. And when delta G is positive, it's not. And basically what we did was related all these signs in the chart up here to create this new value called delta G. And the equation for this is delta G is equal to delta H minus T delta S. Now, a couple things that are super important for this. Delta G and delta H are almost always in kilojoules per mole. Almost always in kilojoules per mole. But S is almost always given to you. S is almost always given to you in joules per mole. And then Kelvin. Kelvin will cancel out with our temperature units here. So please don't forget to convert this to kilojoule. Convert to kilojoule. But all the experiments and equations that I showed you in Unit 6 when we did thermochemistry still apply to this. So you can actually determine the value of delta S for a reaction by doing like products minus reactants. And you can also do this for delta G as well, which is what is represented here with this thermodynamic equation, products minus reactants and products minus reactants. Now, I do want to point out that technically this equation only below should only be used at 25 degrees Celsius. But guys, if they give you delta GF, it's going to be products minus reactants. That's what you're going to use for that particular problem, for that particular value. Now, we can relate this to K, the equilibrium expression. Remember that delta G is referring to being a reaction being spontaneous or not. So another way we could kind of look at this is that if delta G is negative, that must mean that K is greater than 1. Remember that products over reactants is how we get the equilibrium constant K. So delta G being positive, this must mean that K is less than 1. And there actually is a relationship between delta G and K, and that is delta G is equal to negative RT ln of K. R here is the universal gas constant, but we use 8.314 joules per mole Kelvin. I want to remind you guys that oftentimes G is written in kilojoules, so don't forget to change this. But at the end of the day, T is temperature in Kelvin, and K is the universal, K is the equilibrium constant, and it's unitless. And so, yeah, you're pretty much good to go when it comes to that. Last but not least, electrochemistry. Electrochemistry is the last thing that I'm going to go ahead and talk about today. You guys are doing so well, and I'm so very proud of you. The example of free response questions that I've included in the slides are still there, and you have access to them for a long time. You know, if you take the test tomorrow, then you have it for the next couple hours. But I do want to remind you guys that I highly recommend you getting some rest and relaxation tonight. We are going to end with electrochemistry. And electrochemistry is basically the fact that we can utilize these chemical reactions to do work for us. Basically, whenever I literally just had a battery here, but I don't have it anymore. Batteries are chemical reactions. And what we do is we force the electrons out through some sort of wire to do work for us. So that's what electrochemistry is going to be. We're going to be looking at redox reactions for this. And remember, a redox reaction is when a chemical reaction transfers electrons. So let's go ahead and check this out. We're going to look at two redox reactions here. And the two redox reactions we're going to look at are zinc 2+ gaining 2 electrons to turn into zinc, and copper 2+ gaining 2 electrons to turn into copper. As far as this goes, we have a couple ways of measuring these chemical reactions in terms of their electrical potential. And the way we do this is called the standard reduction potential. And it's represented by E red, and we call and we note the units and volts. So negative 0.76 volts for zinc, and the cell potential for copper here is going to be 0.34 volts. For this chemical reaction, in order for us to look at a spontaneous reaction, we want our reaction to be as positive in terms of its voltage as possible. So what we're actually going to go ahead and do here is invert the zinc reaction and then add up our overall reactions. Now, I do want to point out that the standard reduction potential here are intensive properties. So if I were to multiply this reaction by a coefficient, getting 4 and 2, this value does not change, okay? So you don't multiply, when you multiply these reactions by coefficients, the cell potential, the standard reduction potential does not change. So what I'm gonna go ahead and do is invert this reaction, and this gets zinc now being oxidized and creating 2 electrons here. And what the new cell potential for this second reaction is going to be positive 0.76 volts. So while manipulating the reaction or changing the direction of the reaction does change the sign of this, once again, the coefficient will not multiply that reaction there. 2 electrons on opposite sides end up canceling out, and the sum of this reaction is going to be copper 2+ plus zinc makes zinc 2+ plus copper. So the copper, right, was still reduced, and the zinc is now being oxidized. The cell potential for this new reaction is just these two values added up, so it's 1.10 volts. And so what I wanted to quickly do here is show you an example of these values here. So I'll let you check that one out on your own. But a great example is something along the lines of this. They used to give you massive lists of standard reduction potentials, excuse me. Now they just give you short lists, and you go, oh, thank God. I don't have to go through that massive list anymore. So what we want to go ahead and do, since we're trying to calculate the cell potential for this chemical reaction, we want to try to find chemical reactions that actually have the things that are being oxidized and reduced. And when we check this out, we see that zinc oxide is in this reaction here. And it seems like oxygen gas is in that first reaction. Notice that for this particular question, we don't need to have this one or this one. And this will sometimes be the case. Sometimes you don't need to use the data provided to you. Notice that, remember, a lot of chemical questions on the AP test have multiple parts. And I believe on the 2015 number 1, you still need to do and use these cell potentials in a later question. So in order for us to actually answer this particular question, what we need to go ahead and do is manipulate these values here. And we see that zinc is actually on the reactant side and zinc oxide is on the product side. Notice that the coefficients are manipulated, are changed here. But don't fret. Remember, when chemical reactions are multiplied by coefficients, the value for this cell potential does not change. Because the second chemical reaction does flip, the second chemical reaction value becomes positive, and essentially we get 1.31 plus 3.4, giving us a cell potential of 1.65. So I'm going to go ahead and pause here and kind of let you guys breathe a little bit, because I kind of did a home stretch where I just sprinted to the very end. And I just want to say that I so appreciate you guys sticking around for this whole time. I can't even begin to tell you how special it is to teach, it seems to me, a couple thousand students based on what's the numbers here. And I just am so touched. I'm so appreciate everything. You have access to all of these slides. You have access to everything that I've talked about. And if you want something to do at the very end, this is something that is really fun. I'll show you the first example here. This is a game I played last year with my AP Chem students, and I'll probably play it again with them this year. What I do is I provide you with a familiar graph from each unit all over the place, but I don't give you any labeled axes. What you need to do is try and justify what that graph is talking about. Being able to recognize these graphs is such an important thing on the AP test. And like I said earlier with the integrated rate laws, almost the second you see them, you know what question it's going to be asked. And as you go through them, what you can do is say, oh, okay, I think I know what this bar graph represents, and see if you can get that right. This particular bar graph represents the mass spec data. And if you kind of click through, you can definitely see all the important pieces of information that is related to that. Once again, I want to say thank you so very much from the bottom of my heart. My name's Wes Winter, and I love teaching chemistry. It's so much fun. You can find me on the Discord channel, which I know a lot of you are still typing in, and I want to say thank you so very much. Thank you so very much. If you have any questions, feel free to reach out for the rest of the evening. Everyone, I'm sure, is going to be on here. I know it's still pretty early on the California side of things. On the East Coast, can you guys do me a favor? Can you please get a little bit of rest? I wanna show you something here, only because you guys are making me crack up with all the Discord stuff. Hold on. I gotta get to the end. I'm rapidly clicking through. Hold on. All right, here we go. It'll be here somewhere. Good Lord, how many slides did I make? I made a lot of slides. I want to point out that if you continue going through the slide sets, a lot of the slide sets are stuff that I've talked about today, okay? So don't feel like it's something you don't know. You totally do know it. And this is my last slide I want to show you. Yeah, here we go. That's right. You have been visited by the good sleep chihuahua. You're going to be blessed with cozy, restful sleeps. But only if you comment sleep type buffer. What is this, like a mom forward? Don't forget to eat some really good food today. And I just so super appreciate it. You can email me at wes@fiveable.me. That's the email that we have for here. And just kick so much butt tomorrow. Oh my God. You guys know this. I can't even begin to tell you. When I was in high school, I would listen to like my my songs beforehand. I just like get into the zone, and you're gonna crush it. And like Amanda said, this score does not define you. Know that you are resilient people. You are working so very hard to learn a very difficult subject, and you've done it. Like after tomorrow, you're done with AP Chemistry, and I bet that feels so incredibly awesome. Thank you so much. Kick some butt. I'm proud of you all. And yeah. Rufus is not taking the test tomorrow. he already took it and he got a 5. Wait, hold on. Sleep type buffer. Oh my god, so many sleep type buffers. I love it. Oh, you guys rock. You guys are cracking me up. Good luck tomorrow, guys. All right, that's it for me. I'll see you later.